In the last months of 1997, a 27-year-old astronomer named Adam Rees finished a calculation he had been building toward for 4 years, and the number that came back was not merely unexpected. It described a universe containing less than nothing at all. He had been trying to measure how much matter exists, every star, every cloud of gas, every particle of dark matter, all of it added together and spread evenly across all of space. The equation returned a negative quantity. Not a small amount of matter, but less than none, which in any laboratory on Earth is the sort of result that means you have made a mistake somewhere, and the only question is where. So he went looking for it. He checked the brightness measurements, the corrections for dust, the way each explosion's light had been fitted and calibrated. He checked for weeks, and the team he was racing, a rival group headquartered up the hill from his office at the Lawrence Berkeley National Laboratory, who would have been perfectly happy to watch him fail, was working through its own data at the same time and arriving at the same impossible place. Neither of them had made a mistake. What they had found between them was that the expansion of the universe is not slowing down. It is speeding up. Every year, the distance between one distant galaxy and another grows a little faster than it grew the year before. To understand why that stopped 2 rooms full of professionals cold, you have to know what they had been expecting to find. That the universe expands at all had been settled since 1929. Galaxies are moving apart from one another, and the further away a galaxy is, the faster it recedes. But everything in the universe has mass, and everything with mass pulls on everything else, and the whole enormous structure has been pulling inward on itself since the beginning. Gravity should be applying the brakes. Through the whole of the 1990s, the open question was not whether the expansion was slowing, but by how much, whether it would coast outward forever, gradually losing speed, or slow enough to stop, turn, and fall back into a single point. The way you settle a question like that is to look at things very far away, because distance is also time. Light from a galaxy 10 billion light-years off has been traveling for 10 billion years, and what you are seeing is not the galaxy, but the era. Both teams were using a particular kind of exploding star, a type of supernova reliable enough in its brightness that how dim it looks tells you how far off it sits. Rees's collaboration was gathering them with the 4-meter telescope at Cerro Tololo, high in the Chilean Andes, where the air is thin enough to see something that detonated before the Earth existed. Collect enough of these at enough distances, and you can reconstruct the entire expansion history of the universe. What the teams found was that the most distant supernovae were too faint, between 10 and 15% fainter than they should have been, which meant they sat further away than they should have been, which meant that space had been carrying them apart faster than anyone had made room for. They had set out to measure how hard the universe was braking and found its foot on the accelerator. Something is pushing space apart. Not a force in the way we usually mean the word, with a source you could point at, but a property that space appears to have simply by virtue of existing, which means the more space there is, the more of it there is to push. The result held up. Other groups repeated it, other methods confirmed it, and in 2011, Saul Perlmutter, Brian Schmidt, and Adam Rees were awarded the Nobel Prize in Physics for the discovery. Here is what that discovery did to the inventory of everything. Take the entire contents of the universe and sort it into 100 equal shares. 68 of those shares are the thing doing the pushing. 27 are dark matter, which we have never detected directly and know about only because galaxies spin as though it were there. 5 shares are ordinary matter, the kind that makes rock and water and air and people. And of those 5, something close to half of a single share is starlight. Every star in every galaxy, in every photograph ever taken, all the way back to the first plate exposed at the first observatory. Everything our species has ever seen, named, catalogued, or imaged amounts to roughly half of 1% of what is actually here. We call the largest share dark energy, and the difficulty is not that we know nothing about it. We know a great deal. We know how much there is, to within about 1%. We know that its density does not thin out as the universe grows, which is a strange behavior and rules out most of the obvious explanations. We know roughly when it took control, and we have watched it behave consistently across billions of years of cosmic history. It has been measured, weighed, and tracked backwards in time. We simply cannot say what it is. The acceleration has been running for something like 6 billion years. It was already underway while the Earth was still assembling itself out of dust and rubble. It continued through every extinction, every ice age, every human life that has begun and ended, and not one of them had any way of knowing. And then a few dozen people, working in offices and on mountaintops with instruments built by other people they mostly never met, found out. Not in some distant century, but across the span of about 10 years. Most of them are still alive. Some of them are still working. You could have shaken their hands. That seems worth sitting with for a moment. The universe kept this to itself for 6 billion years, and then it stopped. Before we go back to the beginning of all this, and the beginning runs further back than 1997, further back even than Hubble, there is a small request. If you find your way back to these recordings, subscribing genuinely helps. Not for any dramatic reason. It simply means the next one finds you without you having to go looking. And there is one thing worth asking. These tend to be listened to late, in the dark, in rooms a long way from wherever this was recorded. So if you are still awake enough to type, leave a comment saying where you are and what time it is where you are. Say what brought you here tonight, whether you came wanting something specific about the universe or whether you just wanted a voice in the room. They all get read. It is one of the better parts of doing this. Then let it go. There is nothing here you need to hold on to, and no test at the end. Falling asleep partway through is not a failure of attention. It is more or less the point. Now, to understand why a negative number frightened 2 teams of professional astronomers badly enough that both spent months trying to make it disappear, you have to go back much further than a Berkeley office in 1997. You have to go back to a time when the universe was not thought to be moving at all, when stillness was simply the assumption held so firmly that the most careful physicist of the 20th century quietly rewrote his own equations to protect it. He did it in 1917. He was uneasy about it for the rest of his life, and the term he invented to hold the universe still turned out, 80 years later, to be the thing pulling it apart. The trouble with the field equations, from Einstein's own point of view, was that they refused to sit still. He had completed general relativity in November of 1915, and it remains the most beautiful piece of work he ever did, a description of gravity not as a force pulling across empty distance, but as the shape of space and time themselves, bending around anything with mass. 2 years later, he turned it on the largest possible subject. Not a planet, not a star, but everything at once. And the mathematics came back with an answer he had no interest in receiving. A universe governed by these equations could expand, it could collapse. What it could not do was stay as it was. You have to be careful about what the word universe meant in 1917. It meant the Milky Way. Astronomers had catalogued a great many faint spiral smudges and argued about them for decades without settling whether they were clouds of glowing gas somewhere inside our own system or something else altogether, and that question would not be answered for another 6 years. So the universe, as Einstein understood it while writing, was one collection of stars. Individual stars drifted. The system as a whole gave every appearance of sitting exactly where it was, and had given that appearance for as long as anyone had been keeping records. So he added a term. It appears in the equations as the Greek capital lambda, and its job was to push. Gravity draws everything inward toward everything else. lambda was tuned to push outward everywhere at precisely the strength needed to cancel that pull. Balance the two and the universe holds position, not because nothing is happening, but because two enormous opposing tendencies have been matched against each other to the last decimal place. A balance like that is fragile in a way that took some years to appreciate. In 1930, Arthur Eddington showed that Einstein's static universe was unstable. Nudge it in either direction, and it will not settle back, it will run. But that came later. In 1917, the term did what was asked of it, which was to let the sky stand still. 5 years on, a Russian mathematician named Alexander Friedmann worked through the same equations without any interest in preserving stillness, and published the solutions Einstein had declined to take seriously. Universes that expand, universes that contract, universes that do one and then the other. Einstein read the paper and sent a short note to the journal saying that Friedmann had made an arithmetic error. Friedmann wrote to him directly and asked him to check again. Einstein checked, discovered that the error was his own, and published a retraction. 3 years after that, Friedmann was dead of typhoid at 37, having never learned that he had been right about the shape of everything. Then, in 1927, a Belgian priest with a doctorate in physics arrived at the same conclusion by a different road and carried it considerably further than anyone else had. Georges Lemaitre had studied under Eddington at Cambridge and spent a year at Harvard, which meant he understood both the mathematics and the observations, a combination that was rarer than it sounds. His paper did 3 separate things. It described an expanding universe. It showed that in such a universe, distant galaxies would appear to recede in direct proportion to how far away they were, so that a galaxy twice as distant retreats twice as fast. And it produced an actual number for that rate, calculated from redshift measurements that had already been published by an American astronomer named Vesto Slipher, set against the best distance estimates then available. That proportional relationship is the one that would carry Edwin Hubble's name for the rest of the century, and go on carrying it into every textbook written since. Lemaitre had it in 1927 in print with a coefficient attached. He published it in the Annales of the Scientific Society of Brussels in French. It was not an obscure journal in Belgium. Outside Belgium it was close to invisible. He brought the work to Einstein at the Solvay conference in Brussels that same year, and was told by his own later account that his calculations were correct and his physics was abominable. 4 years later, the monthly notices of the Royal Astronomical Society decided the paper deserved an English readership and arranged a translation. When it appeared, the section containing the velocity-distance relationship and the expansion coefficient, the passage that established Lemaitre's claim to the whole thing, was simply not there. If you had been a working astronomer in 1931 reading the English version, nothing in it would have suggested that anything was missing. For 80 years, the obvious explanation was that somebody had taken it out. The motive was not hard to imagine. By 1931, Hubble had published his own version of the relation and become internationally famous for it. And an editor quietly protecting the priority of a distinguished astronomer is an entirely ordinary kind of misconduct. In 2011, the astrophysicist Mario Livio went into the Royal Astronomical Society's archives to find out who had done it and found a cover letter that had been sitting there the entire time. Lemaitre had translated the paper himself. He had removed the passage himself, and he had explained his reasoning in the letter. By 1931, Hubble's observations had produced a better measurement of the expansion rate than his own estimate from 4 years earlier, and he saw no value in reprinting a figure he knew to be worse. He gave away his claim to one of the defining discoveries of the century on the grounds that somebody else's numbers were more accurate than his. Which brings us to the most quoted sentence in the history of cosmology, and to the reasonable possibility that nobody ever said it. You have almost certainly encountered the line. Einstein, faced with the evidence that the universe had been expanding all along, is supposed to have called the cosmological constant the biggest blunder of his life. The source is George Gamow, a physicist and an unusually gifted popular writer, who put the remark in a Scientific American article in 1956 and repeated it in his memoir 14 years later. Einstein had died in 1955. The sentence has not been found anywhere else. It does not appear in his published work, his correspondence, his notebooks, or in the recollections of the people who worked alongside him. Livio went looking for that too, and concluded that Einstein probably never said it. What is documented is the discomfort. He dropped the term as soon as the observations allowed him to, and he wrote about that decision more than once. The unease is real. The sentence is something else, and the sentence describes the wrong error anyway. Taking lambda out was not the mistake. The mistake, if we are going to name one, happened at the other end, in 1917, when a man with every reason on earth to trust his own mathematics decided that the mathematics had to be wrong because the sky looked quiet. All of this, the patch, the retraction, the deleted paragraph, the argument in Brussels, was conducted on paper by men reasoning about a universe that none of them had gone out and measured. They were working from numbers other people had collected. Lemaitre's coefficient rested on them. Hubble's law would rest on them. And Vesto-Slipher, who had gathered those numbers one long exposure at a time beginning in 1912, was not really part of the conversation at all. He was on a hill in Arizona, in the cold, in the dark, photographing objects that nobody on Earth could yet identify, and getting results that should have settled the argument before it started. Photographing a faint object gathers all of its light into a single point on the plate. Taking its spectrum does the opposite. The light is spread along a strip and sorted by wavelength, so that each part of the image receives only the narrow slice of the total that happens to be its own particular color. An object you can photograph in an hour will hold you for 40. Percival Lowell had asked for the work, and he had asked for it in support of an idea that was wrong. Lowell believed the spiral nebulae were solar systems in the act of forming, clouds of gas and dust collapsing into planets, which would have made them nurseries for worlds like this one. He wanted spectra to prove it. He handed the job to his assistant, an Indiana farmer's son named Vesto-Slipher, who had arrived in Flagstaff in 1901 on a temporary appointment and would still be there half a century later. If you want to understand Slipher, picture the dome in February. Lowell Observatory stands on a hill above the town at 7,000 feet, and the building is not heated, because warm air moves and moving air destroys the image. So the work is done cold. He sat at the eyepiece with his hand on the controls, holding a smudge he could barely see against a slit narrower than a hair, correcting the drive in small increments as the earth turned beneath him, for as long as he could stand it. Then he closed the shutter, put the plate away, and came back the following night to continue the same exposure. Some of them ran 20 hours, some ran 40. The faintest took 80 hours of accumulated darkness spread across weeks of usable weather to produce one measurement of one object. On the 17th of September 1912, he developed a plate of the Great Spiral in Andromeda and measured where its lines had fallen. They were in the wrong place. Every line had shifted toward the blue end of the spectrum, and the size of the shift meant the thing was coming toward us at roughly 300 kilometers per second. Nothing had ever been clocked at anything approaching that. The fastest stellar motions on record ran to a few tens of kilometers per second, and here was a figure, an order of magnitude beyond them, produced by an object that nobody on Earth could identify. Slipher's first assumption was that he had made an error somewhere. He checked, repeated the measurement, and it held. Then he went after the rest, and over the following 5 years a pattern emerged that was considerably stranger than the original result. Andromeda was approaching. Almost nothing else was. Of the 25 spirals he had measured by 1917, 22 were retreating, several of them faster than 1,000 kilometers per second, and the overall impression was of a sky quietly abandoning us in every direction at once. When he presented the first 15 of these to the American Astronomical Society in 1914, the room stood up. It is one of the very few recorded standing ovations in the history of that organization, and it was given to a man who could not tell his audience what he had measured. He had the velocities. He did not have the objects. The question of what the spirals actually were, glowing clouds inside our own system or separate systems of stars at distances nobody could estimate, was formally argued in Washington in April of 1920, in a session remembered ever since as the Great Debate. Harlow Shapley held that the Milky Way was the whole of creation. Heber Curtis held that the spirals were galaxies in their own right. Neither man moved the other, and the audience went home without a verdict because the question could not be settled by argument. It could only be settled by measuring the distance to one of them, and there was no way to do that. Which is the other half of this? And it had already been solved 4 years before Slipher opened his shutter, by someone who was not permitted near a telescope. Here is the difficulty with distance. You can measure how bright a star looks. You cannot measure how bright it is. A faint point of light might be a small dim star close by, or an enormous brilliant one very far away, and from where you are standing, those two possibilities produce exactly the same dot. Harvard College Observatory had accumulated hundreds of thousands of glass photographic plates by the turn of the century, and employed a group of women to measure them. They were called computers, which was then a description of the work rather than a machine. They catalogued stars, classified spectra, and recorded brightness at something in the region of 30 cents an hour. Henrietta Swan Leavitt joined them as an unpaid volunteer in 1893 and was eventually put on the payroll. She was assigned the variable stars, the ones whose brightness rises and falls on a repeating cycle, and she turned out to be remarkably good at finding them. In the Magellanic Clouds alone, she identified 1,777 and published the catalogue in 1908. She had lost most of her hearing to an illness in her 20s and worked, by every account of her, in near silence. Then she noticed something about the small Magellanic Cloud that nobody else was in a position to notice, because nobody else had spent years looking at the same patch of sky. The small cloud is a single object. Everything inside it sits at essentially the same distance from us. Its depth is trivial compared with how far away the whole thing lies, which means that within its borders, the one variable that wrecks every brightness measurement in astronomy has been held still. If one star in the small cloud looks brighter than its neighbor, it is brighter. Distance cancels out. Working through her own catalogue with that in mind, she found that the variables with the longest cycles were consistently the most luminous, and that the relationship between the two was not loose or approximate. It was tight enough to draw as a line. Time how long one of these stars takes to brighten and fade, and you know how much light it is genuinely producing. Set that against how much light is arriving here, and the shortfall is distance. That is the foundation of every distance in astronomy beyond our own immediate surroundings. It is how the true size of the Milky Way was eventually established, how the spirals were finally placed outside it, and how the expansion rate of the universe is measured to this day. She published it in 1912 in a 4-page circular from the observatory. The document carries the signature of Edward Pickering, the director. It opens by noting that the following statement has been prepared by Miss Leavitt. What she had built, strictly speaking, was a ruler with perfect proportions and no numbers written on it. It could establish with real precision that one star was 4 times further off than another, but converting that into light years required somebody to independently measure the true distance to a single Cepheid by other means and fix the scale. That one number, sitting at the very bottom of the entire structure, is where all the trouble would eventually come from. Leavitt died of cancer in 1921 at 53. 4 years later, a member of the Swedish Academy began drafting a nomination for her Nobel Prize and had to abandon it when he learned she had been dead since before he started. The prize is not awarded posthumously. She never operated a telescope. The observatory did not allow it. So by 1920, the two halves of the answer were sitting in separate buildings on opposite sides of a continent. In Arizona, there were velocities, 24 objects, most of them in retreat, some moving at speeds that made no sense against any known physics. In Cambridge, Massachusetts, there was a method for converting brightness into distance, finished and published, and waiting for somebody to aim it at those same objects. Put the two together and you have the expansion of the universe. What it took was a bigger telescope than Slipher's, a man willing to use Leavitt's ruler on objects nobody had yet proved were outside our galaxy, and one small error near the base of the scale that nobody would find for another 30 years. On the night of the 2nd of November 1917, the 100-inch telescope on Mount Wilson was pointed at the sky for the first time, and it appeared to be a catastrophe. George Ellery Hale had spent 11 years getting the thing built. The glass blank had been cast in France, arrived full of bubbles, and been ground and polished for years by men who had never worked on anything that size. It was the largest telescope on Earth by a wide margin. And when Hale looked through it at Jupiter that first evening, the planet came apart into 6 or 7 overlapping ghosts, smeared across the field like a badly printed photograph. He went back down the mountain believing that a decade of his life had been wasted on a mirror that could not focus. The dome shutter had been left open during the day. Sunlight had fallen on the glass and warmed it unevenly, and warm glass does not hold a shape. They came back at 3 in the morning after the mirror had spent 6 hours cooling in the mountain air, and the image of Jupiter was the sharpest anyone had ever seen. Nothing about the instrument had changed. One quantity had been wrong, invisibly, and the entire output of the machine had been worthless because of it. It is worth holding that in mind, because the telescope was about to do it again on a very much larger scale. Edwin Hubble arrived at Mount Wilson in 1919, fresh out of the army, and set about the problem that the Great Debate had left unresolved. In October of 1923, he took a plate of the spiral in Andromeda, looking for novae, and found what he took to be one. Comparing it against earlier plates, he realized it was not a nova at all, but a variable star, brightening and fading on a cycle of about 31 days. On the plate, he crossed out the letter he'd written and marked it instead with 3 characters, VAR, and an exclamation mark. A 31-day cycle, run through Leavitt's relation, gives a luminosity. Set that against how faint the star looked, and you get a distance, and the distance Hubble got was around 900,000 light-years. The Milky Way, on the best estimates then available, was perhaps 100,000 across. Whatever Andromeda was, it was nowhere near us. The debate was over, settled by a single star on a single plate, using a method published 11 years earlier by a woman who never saw it used. The velocities came from elsewhere. Most of them had been measured in Flagstaff and published years before, and the rest came from a man on the mountain named Milton Humason, whose route into astronomy was the least likely in the profession. He had left school at 14. He had worked as a bellboy at the hotel on Mount Wilson, then as a mule packer, hauling lumber and steel and eventually parts of the telescopes themselves up the trail on the backs of animals. He took a job as a janitor at the observatory to stay on the mountain, then became a night assistant, and turned out to have an extraordinary gift for the most punishing work in the building: coaxing spectra out of objects almost too faint to find. The man who had carried the equipment up the mountain ended up operating it better than almost anyone. In 1929, Hubble published the result. 46 objects appear in the paper. For fewer than half of them did he have a distance he would have defended individually. He plotted velocity against distance and drew a straight line through the scatter, and the line said that a galaxy twice as far away recedes twice as fast. If you had been shown that graph in 1929 with its handful of points and its considerable spread, you would have been entirely within your rights to decline to draw a straight line through it at all. The galaxies barely reached 6 million light-years. The scatter was substantial. Hubble drew the line anyway, with more confidence than the data strictly supported, and he was right. The slope of that line was the number, 500 kilometers per second, for every megaparsec of distance, meaning that for every 3.25 million light-years further out you looked, galaxies were retreating 500 kilometers per second faster. Now run it backwards. If everything is flying apart at a rate proportional to its separation, then everything was closer together in the past, and there is a moment when the separation goes to 0. Divide 1 by the slope, and you get the time since that moment. With a slope of 500, the answer comes out at roughly 2 billion years. That is the first measurement anyone ever made of the age of the universe, and it was a disaster. Geologists had been dating rocks by radioactive decay since before the war, and their numbers were climbing steadily. By the end of the 1920s, the oldest minerals were coming in at something close to 2 billion years themselves. Within another 2 decades, the figure would pass 3 billion and eventually settle near 4.5. Hubble's universe was, on the most generous reading, exactly as old as the rock the telescope was bolted to. On any less generous reading, it was younger. A universe that had come into being some time after one of its own planets had cooled. The relation was almost certainly right. The number attached to it could not possibly be. And there was no obvious place to look for the error, because every step of the reasoning had been done carefully by people who knew what they were doing. The answer took until the Second World War, and it arrived because of a blackout. Walter Baade was a German national living in Pasadena, and when the United States entered the war, he was classified as an enemy alien and confined to the area around the city. He was permitted to keep working. Nearly everybody else at the observatory left for military research, which meant that the finest telescope in the world was suddenly available almost every night to the one astronomer who was not allowed to go anywhere. And Los Angeles, 40 miles away, had gone dark. The city that had been slowly brightening the sky above Mount Wilson for 30 years switched off its lights, and the seeing conditions became the best they had ever been or would ever be again. Baade used them to resolve individual stars in the crowded central region of Andromeda, something no one had managed before. What he found was that the stars there did not match the stars in the spiral arms. They were a different sort, older, redder, differently distributed. He had discovered that a galaxy contains 2 distinct stellar populations with different histories and different properties, and among the things that differ between them are the variable stars. The Cepheids Hubble had used in Andromeda belonged to one population. The variables that Leavitt's relation had been calibrated against belonged in significant part to the other. They followed a different brightness law. Everything measured with the wrong one had come out systematically too close. Baade announced it at the meeting of the International Astronomical Union in Rome in 1952, and the distance to every galaxy beyond our own doubled overnight. So did the age of the universe. Andromeda went from 900,000 light-years to something closer to 2 million. It still was not enough. A few years later, Alan Sandage found a second error underneath the first. Some of what Hubble had taken for individual bright stars in distant galaxies were not stars at all, but glowing clouds of ionized gas, far larger and far brighter than any single star, which had made those galaxies look much nearer than they were. That correction took another substantial bite out of the number. Two separate mistakes, both of them sitting near the bottom of the measuring chain, both of them invisible to a generation of extremely capable people. You would not have caught them either. The observations were sound, the arithmetic was sound, the instrument was the best on the planet, and the answer was wrong by a factor of about 7 for 30 years because of an assumption nobody knew they were making. The number has been falling ever since. It has not finished falling, and the argument about where it settles is not over. But notice what survived. Every correction moved the slope. Not one of them touched the relation. Galaxies recede in proportion to their distance, and that has held through every revision of the scale from 1929 to the present day. Which leaves the question the arithmetic never answered, and which almost everybody gets wrong on first hearing. If every galaxy is running away from us, and the distant ones are running faster, then we appear to be standing at the center of a general retreat, and there is nothing whatsoever special about where we are standing. The picture that just formed in your head is wrong in an interesting way. The galaxies are not really the things that are moving. There is a reason Hubble's line had to be straight, and it has nothing to do with the universe being tidy. Suppose the recession had gone up with the square of the distance instead, so that a galaxy 4 times further away retreated 16 times faster. Measured from here, that would look perfectly consistent, a clean curve, no contradictions. But carry the same measurements out to any other galaxy and work the sums again from there, and the pattern comes apart. You would find a different law, and the difference would tell you exactly how far you had traveled from the one place in the universe where the simple version held. A relationship like that has a center built into it. Straight proportion is the only relationship that survives a change of address. If every galaxy recedes in direct proportion to how far away it is, then an astronomer on any galaxy anywhere measures precisely the same thing. The same law, the same slope, the same impression of sitting still at the middle of a general retreat in all directions, which means that finding ourselves at the center of it tells us nothing whatsoever, because everybody is. That much is geometry, and it settles the question of where. It does not settle the question of what is actually retreating. And here the honest answer is that the mathematics was finished a century ago, while the English has never quite caught up. The phrase in general circulation is that space itself is expanding. Plenty of working cosmologists use it, and it is a defensible way of putting things. It is also the source of nearly every misunderstanding anyone carries about this subject, because it invites a picture of space as a material, something with a grain to it, being pulled, dragging galaxies along the way a tablecloth drags cutlery. Other cosmologists prefer to describe exactly the same geometry as galaxies simply moving apart from one another, and argue that the fabric picture causes more confusion than it resolves. Both camps make identical predictions about every measurement that has ever been performed. The disagreement is about vocabulary, not physics. What nobody disputes is the substance of it. The distance between two galaxies that are not holding on to each other grows with time at a rate proportional to how far apart they already are. And nothing at all is expanding inside the things themselves. You are not expanding. That deserves saying plainly, because the usual explanation for it is wrong. It is often said that the bonds in your body are strong enough to resist the expansion, as though there were a persistent outward tug that chemistry has to work against. There is no such tug. Expansion is not a force. It is a description of how the average separation between unattached things changes across enormous distances, and where things are attached, that description does not apply. Not weakly, not at some reduced rate. It is simply not what is going on there. So the Earth is not growing. The gap between here and the Sun is not growing. The Milky Way is not growing. It is bound by its own gravity, and has been for the overwhelming majority of its existence. Even the local group, our galaxy, Andromeda, the spiral in Triangulum, and something like 80 smaller companions, is held together tightly enough that it takes no part in the expansion whatsoever, which explains the measurement that set all of this in motion. When Slipher developed that plate in 1912 and found Andromeda approaching at 300 kilometers per second, he was not looking at an exception to a law that had not yet been discovered. He was looking at something the law had never applied to. Andromeda sits about 2.5 million light-years away. It is bound to us, and it is falling toward us under ordinary gravity. The two galaxies are going to collide, and no amount of cosmic expansion will intervene. You have almost certainly been handed the balloon at some point. Dots on stretched rubber, air going in, every dot retreating from every other, the distant ones separating fastest. As a demonstration, it does one thing well. It shows that a surface can grow all over without there being any particular point on it where the growing starts. It fails at everything else. A balloon has a center in the middle full of air, and the universe does not have one. A balloon has an outside, a room it is expanding into, and the universe is not expanding into anything. And the whole thing quietly depends on ignoring the 3 dimensions on either side of that rubber skin while living entirely within 2, which is the precise mental move that generates the question of what the universe is expanding into. The loaf of bread with raisins in it is worse still, since dough has both an edge and a middle. The evidence for all of this arrives as color. A wave of light leaving a distant galaxy is stretched by exactly the factor by which the universe grows during its journey. If the universe doubles in size while the light is in transit, the wavelength doubles, and everything in that light shifts toward the red end of the spectrum. It is not the sound of an ambulance dropping in pitch as it goes past. Nothing is being outrun. When an astronomer says a galaxy sits at redshift 1, the statement is quite specific. That light departed when the universe was half its present size, and it has been stretching for the whole of the intervening time. The same arithmetic produces a fact that sounds like a mistake. Beyond a distance of roughly 14 billion light-years, galaxies are receding from us faster than light travels, not appearing to, but genuinely separating at a rate above 300,000 kilometers per second. This breaks no rule. The speed limit in relativity governs objects moving past one another through space, measured locally, in a single place. It has nothing to say about how quickly the separation between 2 remote points can grow when there is a great deal of geometry lying between them. And the consequence is stranger than the fact we can see those galaxies perfectly well. The deep exposures from the James Webb Space Telescope are crowded with objects that were receding faster than light when they released the light now falling on its mirror, and that are receding faster than light today. Which is how a universe 13.8 billion years old comes to be 46 billion light-years across from where you are sitting. The most distant material we can detect sent its light out 13.8 billion years ago, and that light has been traveling ever since, but the matter that emitted it did not wait around. It has been carried outward the entire time, and it now lies something like 46 billion light-years off. What reaches us is a photograph of where it used to be. One last thing is worth noticing, and it is the reason any of this can be known at all. If the expansion applied to everything without exception, if atoms and meter sticks and telescope mirrors and wavelengths of light all grew at the same rate as the distance between galaxies, then none of it would ever be detectable. Every ruler would lengthen in step with the thing it was measuring, and the universe would present itself as permanently unchanged. We can measure the expansion for exactly one reason. The instruments we measure it with refuse to take part. So there is no middle to this, No edge, no outside, and nothing stretching inside anything that is bound. The retreat is real. It is written into the color of every distant galaxy, and it applies only to the emptiness between the things that have let go of each other. Everything after this depends on one remaining quantity, and it is the least philosophical thing in the whole story. It is a number. How fast? The number arrives with peculiar units, and the peculiarity is the entire content of it. Kilometers per second per megaparsec. A speed divided by a distance. Written out, it looks as though somebody has forgotten to cancel something, and the natural impulse is to tidy it into a plane velocity, the universe expanding at so many kilometers a second, the way a car moves down a road. That impulse has to be resisted, because all of the meaning is in the second half. A megaparsec is 3.25 million light years. What the number says is that two galaxies sitting 1 megaparsec apart, with nothing holding them to each other, will find the gap between them widening at around 73 kilometers every second. Two galaxies 10 megaparsecs apart are separating 10 times faster than that. There is no single speed of expansion because the speed depends entirely on how much space you are looking across. It is a rate of growth applied per unit of distance, everywhere, simultaneously. Convert it into a fraction, and it becomes almost comically small. The gaps between unbound things grow by roughly 1 part in 13 billion each year. Across an entire human life, the distance from our galaxy to a remote one widens by something like 6 parts in a billion, a change no instrument standing still could ever register. The expansion is measurable only because it accumulates across distances enormous enough that a fraction that small still adds up to hundreds of kilometers a second. To pin the rate down, you need two quantities for the same object: how fast it is receding and how far away it is. The velocity is the easy half. The shift in the light hands it to you directly, and Slipher was pulling them out in 1912 with a brass spectrograph and an unreasonable amount of patience. Distance is where the difficulty lives. You cannot measure 1 billion light years. There is no instrument that reaches, no technique that spans it, nothing you can lay alongside it. Every distance in astronomy beyond our own solar system is inferred, and the inference is assembled as a chain. At the bottom sits the one genuinely direct measurement available, and it runs on geometry alone. As the Earth travels from one side of its orbit to the other, a nearby star appears to shift very slightly against the more distant stars behind it. Measure that shift, know the width of the orbit, and trigonometry does the rest. The shifts are almost nothing. Proxima Centauri, the closest star to the Sun at 4.25 light years, moves by about 8/10ths of an arcsecond, and an arcsecond is 1/3600th of a degree, the angle a 2-centimeter coin would make if you set it on the ground and walked 4 kilometers away. That is the largest parallax in the sky. Everything else is smaller than that. Before recent decades, the technique gave trustworthy distances out to a few hundred light years, which covers a small patch of our own galaxy and nothing beyond. To go further, you use it to calibrate something brighter. Cepheid variables occupy the second rung. Parallax establishes the true distance to nearby ones that fixes the scale on Leavitt's relation, and the relation can then be turned on Cepheids in other galaxies, out to wherever a telescope can still separate individual stars from the general crowd, which is somewhere around 100 million light years. And there the second rung ends, because beyond it, single stars dissolve into the glow of the galaxy holding them. Each rung is calibrated by the one beneath it. Move the bottom and everything above shifts with it, silently, all the way to the top, which is exactly the failure that had once produced a universe younger than its own planets, and which nobody standing inside the structure had been able to see. So the argument that followed was not a quibble about decimal places. It ran for 30 years and became genuinely unpleasant. Alan Sandage had worked as Hubble's observing assistant at Mount Wilson and inherited the program outright when Hubble died in 1953. He spent the remainder of his career refining the measurement, and by the 1970s he had settled on a value near 50 kilometers per second per megaparsec, which implied a universe around 20 billion years old. Comfortable, unhurried, with ample room for the most ancient stars. Gérard de Vaucouleurs, working from Texas, applied the same class of methods to a heavily overlapping sky and got about 100. That is a universe half as old. 10 billion years, which sat uncomfortably close to the estimated ages of the oldest globular clusters, and in some versions of the calculation was actually younger than them. Two of the most capable observers alive, using the same techniques on the same objects, disagreed by a factor of 2 about the age and size of everything, and neither would move. The dispute became known for its temperature as much as its content. Each man held that the other was committing systematic errors, and each said so in print, repeatedly. The field sorted itself into camps, and the camps did not mix easily at conferences. Then the discipline did something that is either a confession of failure or a small masterpiece of pragmatism, depending on your temperament. Cosmologists simply stopped waiting for a verdict. They began writing the Hubble constant as 100 multiplied by a letter, a lowercase h standing for some number between roughly a half and 1, whose value nobody could supply. Results were published carrying that letter through the algebra, so that any given paper would remain correct, no matter which way the argument eventually resolved. An entire branch of physics agreed to express its findings in terms of a quantity it could not measure, and got on with the work. The notation survives to this day. Settling it was one of the reasons the Hubble Space Telescope was built. That is not a flourish added afterwards. When the case was made for lifting a large optical telescope above the atmosphere, 3 scientific programs were designated key projects, the work that would justify the expense. One of the 3 was to measure the Hubble constant to within 10%. A telescope of that cost, placed in orbit, with a substantial share of its early purpose given over to resolving a single number that 2 astronomers had been arguing about since before the instrument was designed. Wendy Friedman led it. The approach was to use the telescope's resolving power to find Cepheids in galaxies distant enough to calibrate the brighter indicators that reach further out, and then to work steadily outward from there. It occupied most of a decade. The result was published in 2001, 72 kilometers per second per megaparsec, give or take 8. Neither man had been right. The answer landed almost precisely between the 2 positions, closer to the middle than either camp had ever been prepared to entertain. The bottom rung has since been rebuilt from scratch. The Gaia spacecraft, launched by the European Space Agency at the end of 2013, spent 11 years doing almost nothing except measuring the positions of stars over and over, from a stable point 1.5 million kilometers out beyond the Moon. It catalogued close to 2 billion of them. Its precision is quoted in micro-arc seconds, millionths of the angle that coin makes at 4 kilometers, which is roughly the feat of picking out the width of a single human hair from 1,000 kilometers away. Cepheid calibrations that had once rested on a handful of nearby stars now rest on thousands, each one measured by geometry alone. Re-anchoring the bottom, though, does nothing to extend the top. Cepheids still give out around 100 million light-years, and 100 million light-years is a very small sample of the universe, enough to establish how fast things are separating in our own neighborhood, nowhere near enough to ask whether that rate has been the same throughout cosmic history. Answering that requires seeing across billions of light-years, which means finding something so violently bright that a single one of them can be picked out halfway to the edge of what we can observe. Such a thing exists. It is what happens when a star roughly the size of the Earth finally loses the argument with its own gravity. It is not, strictly speaking, a star anymore. Nothing is burning inside it. A white dwarf is what remains after a star of moderate size, anything up to roughly 8 times the mass of the Sun, has worked through its usable fuel, swollen, and thrown its outer layers off into space. What survives is the core, a sphere of carbon and oxygen, the ash left over from the final round of fusion, with nothing left to fuse and no way of generating new energy at all. It does not produce light so much as leak it. Everything a white dwarf will ever radiate is heat it already possesses, escaping slowly over billions of years. Picture something about the size of the planet you are sitting on, containing close to the entire mass of the Sun. The obvious question is why it does not immediately collapse, and the answer is one of the stranger consequences of quantum mechanics. Electrons cannot be pushed into identical states. Crowd them tightly enough and they begin to resist, not because they repel one another electrically, though they do that as well, but because the arrangement itself is forbidden. The pressure this produces has nothing whatever to do with temperature. A white dwarf could cool to absolute zero and it would not shrink by a single meter. That resistance supports a body with a density around 1,000,000 times that of water. A teaspoon of the material, brought here and set on a kitchen table, would weigh about 5 tons. And it behaves backwards. Add mass to an ordinary object and it grows. Add mass to a white dwarf and it shrinks. The additional weight compresses the electrons further. They push back harder, and the whole sphere settles at a tighter radius, which means there has to be a point where this stops working. That point was calculated in 1930 by a 19-year-old named Subramanian Chandrasekhar aboard a steamer from Madras to England on his way to begin postgraduate work at Cambridge. Somewhere between India and Europe, he worked out that in a sufficiently massive white dwarf, the electrons would be pushed to speeds approaching that of light, and that at those speeds, their capacity to resist further compression begins to fail. Above roughly 1 4/10 times the mass of the Sun, degeneracy pressure simply loses. The limit still carries his name. Most white dwarfs never come near it. They cool quietly for the rest of time and nothing further happens to them. But a great many stars are born in pairs, and a white dwarf with a companion is in an entirely different position because it can take material from the other star, drawing gas across the gap between them and laying it down, gram by gram, on its own surface. As the mass climbs, the star tightens and the interior heats. Somewhere near the limit, the temperature at the center reaches the point where carbon begins to fuse. In an ordinary star, this would correct itself. Fusion releases energy, the gas warms, warm gas expands, expansion drops the density, and the reaction slows. A thermostat that has held the Sun steady for 4.5 billion years. A degenerate star has no thermostat because its pressure does not depend on its temperature. So when the carbon lights, the core heats without expanding, and hotter carbon fuses faster, which heats it further, which drives it faster still. The entire star is consumed in about 2 seconds. Nothing is left behind. A collapsing massive star leaves a neutron star or a black hole. This leaves nothing at all. The whole object is converted in that couple of seconds into a cloud of newly manufactured elements traveling outward at something like 10,000 kilometers per second, and roughly 6/10 of a solar mass of that cloud is radioactive nickel, which is where the light comes from, and it is not what most people picture. The flash of the detonation is over almost at once and is largely trapped inside the expanding debris. What we watch for weeks afterwards is radioactivity. Nickel decays into cobalt with a half-life of 6 days. Cobalt decays into iron with a half-life of 77. That slow, steady release from inside the cloud is what keeps the thing shining long enough to be studied. The light is not the explosion. the light is one element turning into another. The brightness climbs for about 3 weeks. At peak, the object is producing something in the region of 5 billion times the output of the Sun, bright enough that for a period of days it outshines the entire galaxy it went off in. 100 billion stars, and one dead one coming apart, puts out more light than all of them together. That is the property that makes it useful. A single one of these can be picked out across billions of light years in a galaxy that is otherwise barely a smudge on the plate, because for a few weeks it is competing with everything that galaxy contains. There was one remaining difficulty, and it held the technique back for most of a century. They are not all the same brightness. They vary by a factor of a few, which is far more than enough to ruin a distance. Something had to be found that would let an observer tell the bright ones from the dim ones without already knowing how far away they were. The pattern had been spotted before. Bert Rust in 1974 and Yuri Skovsky in 1977 both reported that the brighter explosions appeared to fade more slowly than the fainter ones. It was Mark Phillips, working with observations from Cerro Tololo, who nailed it down properly in 1993 and turned it into something you could use. Measure how far the supernova dims across the 15 days after its peak, and that rate of decline tells you how luminous it actually was. The reason comes back to the nickel. An explosion that manufactures more radioactive nickel is brighter, straightforwardly, because there is more decaying material inside it. But more nickel also leaves the debris hotter and more opaque, and light working its way out of a hotter, thicker cloud takes longer to escape. So the brightest explosions are also the slowest to fade, and both effects trace back to the same cause. The shape of the light curve is reporting the contents of the star. Applied carefully, that correction pulls the scatter down to about 15/100ths of a magnitude, which works out at an uncertainty of roughly 7% in distance. 7% across 10 billion light-years using an object that destroyed itself before the Earth existed. Notice the word that has to be used, though. These are not standard candles. They are standardizable ones, and the difference is not pedantic. A standard candle is identical everywhere, always. A standardizable candle is one whose variation we believe we can predict, using a correction derived from nearby examples and then applied to distant examples on the assumption that distant ones behave the same way. That assumption carries the entire weight of the structure, and it remains an assumption, which brings us to the least comfortable fact in the subject. We do not know what explodes. Two mechanisms have been competing for decades. In the first, the companion is an ordinary star, and the white dwarf strips gas from it steadily until the limit is reached. In the second, the companion is another white dwarf, and the pair spiral inward over hundreds of millions of years, bleeding away their orbital energy as gravitational waves until they merge. The first version struggles with the evidence. If a normal star has been feeding a white dwarf, that star ought to survive the explosion and remain visible, and hydrogen stripped from its surface ought to show up in the spectrum. When the closest Type 1a in a generation went off in the Pinwheel Galaxy, 21 million light-years away, and was caught within hours of detonating in August of 2011, no surviving companion was found and no hydrogen appeared. Whatever exploded had been very compact. The second version has its own trouble. Two merging white dwarfs would not reliably add up to 1 4/10 solar masses. They would produce a spread of masses which threatens the very uniformity the method depends on. Recent work has leaned increasingly toward explosions that happen below the Chandrasekhar limit altogether, set off when a layer of helium on the surface detonates and drives a shockwave down into the core. So the position is genuinely odd. The behavior of these objects is consistent enough to measure the universe with. The explanation for why they are consistent is not settled. The method works better than our account of it does, and every distance in what follows was established using a candle whose wick nobody has conclusively identified, none of which slowed anybody down. By the middle of the 1990s, the pieces were in place. The candle existed, the correction had been published, detectors had improved to the point where distant explosions could be hunted deliberately rather than stumbled across, and two separate teams had telescope time, funding, and a specific objective. Both of them set out to measure how quickly the expansion was slowing down. Neither of them entertained, in any serious way, the possibility that it wasn't. The first obstacle was not physics, it was scheduling. A supernova gives no warning. It appears, brightens over roughly 3 weeks, and fades, and to measure one properly, you need the largest telescopes on Earth pointed at it inside that window, including a spectrum to confirm what kind of explosion it is, which means an instrument booked 18 months ahead by people who submitted proposals for something else entirely. There is no way to apply for observing time on the grounds that something might happen somewhere in the sky at some unspecified point next year. The way around it was devised by a group at the Lawrence Berkeley laboratory that Saul Perlmutter had been running since 1988, and it is the reason everything that follows was possible at all. The method is almost administrative in its cleverness. Immediately after a new moon, with the sky at its darkest, photograph a large number of distant galaxy fields, tens of thousands of galaxies across a few nights. Wait 3 weeks, photograph precisely the same fields again, just before the next new moon, then subtract one set of images from the other. Nearly everything cancels out, and what survives the subtraction are the points of light that were not there before. Some are asteroids, some are flaws in the detector, and a handful are supernovae, caught on the way up rather than the way down. The essential part is that the discovery date has become a matter of arithmetic instead of luck. If you can demonstrate that a batch of new supernovae will exist on a particular Tuesday in March, you can book the follow-up observations in advance and be taken seriously. The least predictable event in astronomy had been converted into something that could be entered in a diary. A second group formed in 1994, assembled largely out of the people who had built the foundation the whole technique rested on. Nicholas Suntzeff and Mark Phillips at Cerro Tololo had spent years running the survey that produced the nearby supernovae everything else was calibrated against. Brian Schmidt, then at Harvard and soon to move to Mount Stromlo in Australia, took charge of the new effort, and Adam Rees ran the analysis. The two groups did not care for each other. Each considered the other's procedures sloppy in specific identifiable ways and was willing to say so, and arguments about who had done what first were still being conducted a decade afterwards. This turned out to be the single most valuable feature of the whole enterprise, because it meant neither team could publish anything without knowing the other would go through it line by line looking for the mistake. What both were chasing was one quantity, the deceleration parameter. Expansion combined with gravity produces a clean expectation. The expansion should be slowing, and the rate at which it slows depends on how much matter the universe contains. Measure the slowing and you have weighed everything. Nobody had a trustworthy figure for the mass of the universe, and this promised to deliver one. The measurement works by comparison. Observe supernovae nearby where the expansion history has had no time to matter, and establish the relationship between redshift and distance. Then observe supernovae far away, where the light has been traveling long enough for that history to leave a mark, and see how far the relationship has shifted. In a decelerating universe, expansion was quicker in the past, so distant objects sit closer than a steadily coasting universe would place them. And closer means brighter. In 1997, the Berkeley group published their first substantial result, built on 7 supernovae. It came out almost exactly as anticipated, A universe carrying enough matter to be slowing down appreciably, perhaps enough to halt eventually. The expected answer, arrived at carefully, with error bars attached. It was wrong, and within a year they would withdraw the conclusion themselves on the strength of more data. Because as the samples grew, the distant supernovae came in faint, not merely closer than a coasting universe would predict, which is what deceleration demands. Further, to see how uncomfortable that is, you have to know what the limiting case was supposed to be. Take all the matter out of the universe, every galaxy, every atom, every particle of dark matter, and empty it entirely. With nothing left to pull on anything, the expansion neither slows nor quickens. It coasts at a fixed rate, indefinitely. That is the greatest distance light from a given redshift can possibly have covered, and therefore the faintest a supernova at that redshift can possibly look. An empty universe is the floor. The supernovae were below the floor. This is why the arithmetic produced an impossible answer. If you insist that matter is the only ingredient and ask the data how much of it there is, the data reply that there is less than none, because even zero does not push the objects far enough away. The negative figure was not a fault in the fitting routine. It was the routine correctly reporting that the model it had been handed did not contain whatever was actually happening. The obvious response is that the supernovae are not genuinely fainter, only apparently so, and there were two ways that could come about. The first is dust. Material spread thinly between galaxies would dim light passing through it, and the further the light had traveled, the more would be absorbed, producing precisely the observed pattern. Ordinary dust can be excluded because it scatters blue light more effectively than red and would therefore redden the supernova as well as dimming them, and the reddening is absent. But a hypothetical dust made of larger grains would dim without reddening, and nothing available in 1998 could rule that out. The second is evolution. These explosions occur in stars, and stars in the young universe formed from material containing far fewer heavy elements. If that alters how a white dwarf detonates, even marginally, even in a way undetectable in the nearby examples, then distant supernovae would be intrinsically dimmer than the ones used to calibrate them, and the entire result would be an artifact of comparing two different populations against each other. Neither objection could be dismissed on the evidence then available. Both teams laid them out explicitly in their own papers, in the sections describing what might be wrong with their conclusion. Brian Schmidt later described his team's reaction to their own result as somewhere between amazement and horror. The High-Z paper went to the Astronomical Journal on the 15th of May 1998 and appeared that September. It rested on 10 newly measured supernovae combined with earlier observations, 16 distant objects in total, weighed against 34 nearby ones, spanning redshifts from about 0.16 out to 0.62. Depending on what one was prepared to assume about the matter content, the evidence for something pushing outward ran between 3 and 4 standard deviations, climbing to 7 or 9 if you also assumed the geometry of the universe was flat. The Berkeley paper was submitted on the 8th of December that same year and published the following summer. 42 distant supernovae reaching out to redshift 0.83 fitted against the nearby sample Cerro Tololo had spent years accumulating. Assuming flatness, they found the matter density at around 28% of the total. The probability that the additional term was greater than 0, folding in every systematic error they could identify, came out at 99%. Two groups that did not trust one another, working with overlapping but distinct samples, separate analysis software, and different calibration procedures, submitted papers 7 months apart saying the same thing. The journal Science named it the breakthrough of the year for 1998. The Nobel Prize followed 13 years later, and its structure is worth noticing. One half went to Perlmutter, The other half was shared between Schmidt and Rees. The committee had to reach a verdict on a priority question the field itself has never entirely resolved, and that division is roughly what the verdict looked like. None of the papers explained anything. They had established a fact: the expansion is speeding up, and the fact demanded a cause, and the cause was entirely unidentified. The mathematics could absorb it without difficulty. There was already a term available, sitting unused in the equations for 80 years, that would do the job perfectly well. But writing a symbol into an equation is not the same as knowing what the symbol refers to. Somebody now had to name the thing, and the man who named it picked his words with real deliberation, precisely in order to stop his colleagues from assuming they already understood what they had found. There were obvious names available, and the trouble with each of the obvious names was that it already contained an answer. Call the thing the cosmological constant, and you have asserted that it is Einstein's term, fixed, unvarying, identical today to what it was 10 billion years ago. Call it vacuum energy, and you have asserted that it arises from quantum fields in empty space. Both were plausible. Neither had been demonstrated, and a name, once it has settled onto something, does a great deal of quiet work afterwards. People stop asking questions that the name appears to have closed. Michael Turner, a cosmologist at the University of Chicago, was the one who ended up choosing at a meeting held in 1998 at Mount Stromlo in Australia, which happened to be the home institution of one of the two teams that had just found the thing. His account of the reasoning is unusually plain. The first requirement, he has said, was to avoid calling it the cosmological constant or vacuum energy, because either way the answer would already have been assumed. After that, it was a question of finding the best short phrase. He settled on dark energy, and the choice was deliberate down to the syllable. It was constructed to echo dark matter, the term Fritz Zwicky had introduced in 1933 for the unseen mass-holding galaxy clusters together. In Turner's own words, the name was extremely intentional. What he wanted was something that would say, "This is a really big mystery, don't jump to conclusions." The parallel is not exact, and the imprecision is worth noticing. Dark matter is dark in a literal sense. It emits no light, absorbs none, and does not interact with light at all. Dark energy is dark in an entirely different sense. It is not that the thing fails to shine, it is that nobody can say what it is. The physics underneath the name is where the real difficulty begins, because nothing in ordinary experience pushes the way this has to push. The phrase that gets used is negative pressure, and the image it produces in most heads is backwards. Negative pressure does not shove outward. Negative pressure is tension, the state of a stretched spring, of a rubber band pulled taut, of water being drawn up the trunk of a tall tree under strain. Stand inside a region of negative pressure, and it would be pulling inward on its own boundaries, not pressing out against them. So the outward push is not mechanical. In a universe filled uniformly with something, there are no pressure differences anywhere, and with no difference there can be no force. Whatever is driving the expansion is not pressing on anything at all. It is gravitating. That is the piece with no equivalent in Newton's version of gravity, and it is the reason the acceleration could be accommodated by existing theory rather than requiring a new one. In Newtonian physics, mass is what attracts, full stop. In general relativity, mass is one entry on a longer list, and pressure is also on that list. Pressure has weight. In ordinary circumstances, the contribution is far too small to notice. The pressure at the center of the Sun is immense by any human standard, and its gravitational effect is a rounding error beside the Sun's mass. But the term sits there in the equations regardless, and it has no preference about sign. Positive pressure adds to the inward pull. Negative pressure subtracts from it. And if the pressure is negative enough, the subtraction wins outright, and the whole gravitational effect reverses direction. The threshold is specific. A substance whose pressure is more negative than -1/3 of its energy density does not attract. It repels. Which leaves the question of why anything would have a pressure like that, and the answer arrives from an unexpected direction. It comes out of bookkeeping. Take a region of space with some quantity of energy in it, and let the region expand. If the energy is in the form of matter, the amount stays fixed while the volume grows, so the density drops. Double the region in every direction, and you have 8 times the volume and 1/8 the density. That is the behavior of every substance you have ever handled. Now suppose there is something whose density does not drop. Expand the region and there is more total energy inside it than there was before, contained within a boundary that has grown. Energy does not simply appear, so it must have been paid for, and the only available payment is work done on the region as it expanded. Follow that requirement through and it yields one exact answer. For the density to hold steady, the pressure must be negative, and its size must equal the energy density precisely. So the two peculiar facts about dark energy are not two facts. They are one fact viewed from either end. Its pressure is negative because its density does not dilute. Its density does not dilute because its pressure is negative. And the value that falls out, pressure equal to minus the energy density, lands comfortably past the threshold where gravity changes sign. That single property decides everything downstream. Matter thins as the universe grows, falling away as the cube of the expansion. Radiation thins faster still as the fourth power because the waves are being stretched at the same time the volume is increasing. Double the size of the universe and the radiation density drops by a factor of 16. Every other ingredient dilutes. This does not. Whatever the density of dark energy was when the universe was 1,000th of its present size, it is exactly the same now. The universe has since grown 1,000-fold in every direction, 1,000,000,000 times the volume, and there is 1,000,000,000 times as much of the stuff at precisely the same concentration. It does not prevail by being powerful. In the early universe it was irrelevant, buried under radiation and then under matter, a negligible term in an equation ruled by everything else. It prevails by outlasting the competition. Everything else thins out. It stays. Cosmologists track all of this with a single ratio: the pressure of a substance divided by its energy density. The quantity is called the equation of state, and it is written as a lowercase w. For ordinary matter drifting slowly and exerting essentially no pressure, the ratio is 0. For radiation, it is 1/3. For anything whose density never changes, the bookkeeping argument forces it to be exactly -1. That number has become the most closely watched quantity in the subject, and the reason is straightforward. If it is precisely -1, then what we are dealing with is a constant, a fixed feature of space, identical everywhere and at every moment in the history of the universe. If it is anything else, even marginally, then it is not a constant at all. It is a field of some description, with its own behavior, capable of changing over time and of having been different in the past, which is where Einstein's term returns, though not quite in the way the story is usually told. When he added lambda in 1917, he placed it on the left-hand side of his equations, among the terms that describe the shape of space-time. That is a claim about geometry. It says that space, by its nature, carries a slight built-in tendency to expand in much the same way that it carries a certain number of dimensions. It is not a thing inside the universe. It is a property of the stage. The modern reading generally moves the term across to the right-hand side, where the contents of the universe are itemized: matter, radiation, everything that carries energy. Placed there, it is not a property of the stage at all. It is a substance filling space, possessing a density and a pressure like anything else in the inventory. The mathematics is identical either way. You can shift the term from one side to the other and change nothing that any instrument could ever detect. But the two placements are statements about completely different kinds of thing, and there is at present no measurement capable of telling them apart. The most popular version of the right-hand side reading is vacuum energy. Quantum field theory holds that empty space is not empty, that fields extend everywhere, fluctuating, never entirely at rest, and that this activity carries an energy which cannot be drained away because there is nothing to drain it from. Energy belonging to space itself, and therefore not diluting when space grows, which is exactly the behavior required. It is an elegant fit. It would close the case entirely, were it not for what happens when somebody tries to calculate how much of it there ought to be. So by the opening years of this century, there was a name chosen specifically not to explain anything. A ratio worth measuring to several decimal places, and an 80-year-old term restored to the equations with its purpose inverted and its address in dispute. What was still missing was the amount. Establishing that the expansion is accelerating tells you something is there. It says nothing whatever about how much. Settling that required a completely different kind of measurement. And when the answer came back, it did not so much adjust the inventory of the universe as overturn it. To a precision better than 1%, we now know what the universe is made of. That ought to strike anybody as an outrageous thing to be able to say. A century ago, the live question was whether anything at all existed outside our own galaxy. 50 years ago, two of the best observers alive could not agree on the expansion rate within a factor of 2. And the ingredient list has since been settled, not estimated, settled to several decimal places, without anyone leaving the planet, collecting a sample, or coming any nearer the material in question than the far end of a telescope. It cannot be done by counting. No census reaches far enough, no survey goes deep enough, and in any case, the majority of what is out there emits nothing whatsoever. What can be done instead is to measure the shape of the universe, because in general relativity, the shape and the contents are the same question asked in two different ways. Put energy into a region and the geometry bends. Measure the geometry carefully enough, and you have measured the energy. The measurement is made on the oldest light there is. For its first 380,000 years, the universe was too hot for atoms to hold together. Electrons could not stay bound to nuclei, so everything existed as a charged plasma, and light could not get through it. A photon released anywhere would scatter off a free electron almost immediately, then again and again, so that the whole universe was opaque. Something like the inside of a fog bank lit from within. Then the temperature dropped past roughly 3,000 degrees and the electrons were captured. The fog cleared over the course of a few tens of thousands of years, and the light that had been bouncing around inside was abruptly free to travel in straight lines. It has been traveling ever since, stretched by the expansion out of the visible range and into microwaves. It arrives here as a faint uniform glow from every direction at a temperature of about 2.7 degrees above absolute zero, and it constitutes a photograph of the universe taken at the instant it became transparent. The photograph is very nearly blank. The temperature is identical across the whole sky to about 1 part in 100,000, but the minute departures from uniformity are the entire point, because they are not randomly sized. Before the fog lifted, the plasma had been doing something quite specific. Gravity drew material into the slightly denser regions. The pressure of the trapped radiation pushed back out. The compressed region overshot, rebounded, and compressed again. The early universe was oscillating, pressure waves of exactly the same kind as sound, running through a medium that filled everything there was. Those oscillations had a strictly limited time in which to develop, precisely as long as the universe took to turn transparent. A wave could travel only so far in that interval, which imposes a maximum size on the resulting patches. When the light was released, the pattern was frozen into it, a characteristic scale printed across the sky as warm and cool regions whose true physical size can be worked out from known physics. That makes it a ruler of calculable length, held at a calculable distance, and the apparent size of a ruler at a known distance depends entirely on the geometry of the space in between. In a positively curved universe, the patches would appear larger than the arithmetic says they should. In a negatively curved one, they would appear smaller. In a flat universe, they show up at exactly the predicted angle. About 1 degree across, roughly twice the width of the full moon. The universe is flat to within a fraction of a percent. Flatness is not a decorative detail. It fixes the total energy density of the universe precisely at what cosmologists call the critical value, the exact quantity required to produce a flat geometry, no more and no less. So the total is pinned down. Then you count what can be identified. The relative heights of the peaks in the pattern reveal how much ordinary matter was present, because ordinary matter feels the radiation pressure and dark matter does not, and the two therefore leave distinguishable fingerprints in the oscillation. Ordinary matter and dark matter together come to about 31.5% of the critical density. The remaining 68.5% is not optional. It is the gap between what the geometry demands and what the matter can supply, and it was arrived at without reference to a single supernova. The instruments improved by orders of magnitude across 3 decades. COBE, launched in 1989, established that the fluctuations existed at all and could resolve nothing finer than about 7 degrees. WMAP, from 2001, brought that down to 1/5 of a degree. Planck, launched in 2009, reached about 5 arc-minutes and mapped the entire sky at that resolution. Its final analysis puts the expansion rate at 67.4 kilometers per second per megaparsec, give or take half a unit, and the composition at roughly 68% dark energy, 27% dark matter, and 5% ordinary matter. That 5% deserves a moment of its own, because it is not where most people assume it is. Stars account for something like half of 1% of the whole. Everything else in the ordinary category, the overwhelming majority of the atoms in existence, the protons and neutrons that make up rock and water and air and bodies, is thin gas spread through the space between galaxies, too diffuse and too hot to shine in visible light, too cool to announce itself clearly in X-rays. For roughly 20 years, this produced an embarrassment known as the missing baryon problem. The theory predicted a specific quantity of ordinary matter. The oldest light confirmed the prediction. And when astronomers added up everything they could actually locate, about 1/3 of it was simply not there. Not dark matter, ordinary matter of the familiar kind, unaccounted for. It was run down using fast radio bursts, intense flashes lasting 1,000th of a second, arriving from galaxies billions of light years off, whose signal is smeared out slightly by any charged material it crosses on the way. The degree of smearing measures how much matter the light passed through. A census published in 2020 found the missing baryons sitting precisely where the models had placed them, in the thin ionized gas between the galaxies. Which brings the accounting round to the largest item on the list and to the most counterintuitive number in the subject. Hold a cubic meter of empty space in your mind. A box a meter along each edge, somewhere out between the galaxies, containing nothing at all. The dark energy inside that box comes to about 6/10 billionths of a joule. A joule is not a grand unit. It is roughly the work involved in lifting an apple from the floor onto a table. This is a billionth of that, distributed through a cubic meter. Converted into mass, it amounts to the equivalent of about 4 hydrogen atoms per cubic meter, in a volume of space where finding even one would be difficult. Take the entire body of the Earth, every cubic meter of rock and iron and ocean from the crust to the core, and add up all the dark energy contained inside it. The total comes to somewhere around 600 billion joules, which is about 10 minutes of output from a single power station. That is the thing accelerating the universe. It does not manage this by being intense. It manages it by being present in every cubic meter of a universe 46 billion light years across in every direction, and by staying at exactly that concentration no matter how much more space there is to fill. Matter is enormously more potent per unit volume, and matter is losing because there is a fixed amount of it being smeared ever thinner. Dark energy is the feeblest item in the inventory, and it is winning on volume alone. All of which now rested on two foundations that had nothing to do with one another. Exploding stars, measured one at a time across billions of light years, said the expansion is speeding up. The oldest light in the universe, measured as a pattern of warm and cool patches, said that 2/3 of the energy budget cannot be accounted for by matter. Neither measurement borrowed the other's instruments, assumptions, or methods. 2 is better than 1. It is not by itself sufficient, and the people who had staked their careers on the result understood that considerably better than their critics did. So they went hunting for other ways of asking the same question, and one of the answers turned out to have been sitting in plain view the entire time, printed across the arrangement of the galaxies for as long as anybody had been bothering to map them. The ringing left 2 marks, and the light carried only one of them. Before the universe turned transparent, the material inside it was not behaving as a single substance. It was behaving as 2, and the difference between them is what makes the second mark possible. Dark matter responds to gravity and to nothing else. It does not interact with light, feels no radiation pressure, and took no part in the oscillations whatever. Wherever there was a slight excess of density to begin with, dark matter simply stayed there and slowly accumulated. Ordinary matter had no such freedom. Protons and electrons carry charge, and in that environment they were locked to the photons, colliding with them constantly, so tightly coupled that radiation and matter moved as a single fluid. When pressure drove that fluid outward from a dense region, the ordinary matter was carried along with it, swept away from the center in an expanding shell, traveling at about 57% of the speed of light. Then the electrons were captured, and the coupling broke. The photons went free, the pressure disappeared, and the shell of ordinary matter that had been riding outward on it for 380,000 years suddenly had nothing pushing it anywhere. It stopped where it was. What this leaves behind is a particular arrangement, repeated everywhere across the universe. At the center of each original overdensity, a concentration of dark matter. Surrounding it, at a fixed radius, a spherical shell of ordinary matter, stranded at precisely the distance the sound had managed to travel before the universe let go of it. Both are places where galaxies preferentially form, which means the galaxies around you are not scattered at random. The effect is extremely faint, because gravity has spent 13 billion years stirring everything together since. What survives is a statistical preference and nothing more. Take any galaxy in the sky, measure the distance to every other galaxy, and there is a very slight excess of pairs separated by roughly 480 million light-years. 147 megaparsecs, the exact distance those waves reached before they stopped. The excess amounts to about 1%. It is not a structure anyone could point at. There is no ring of galaxies anywhere. There are simply marginally more pairs at that separation than chance would supply in every direction, everywhere you look. Detecting a 1% preference requires an enormous catalogue, and the catalogue did not exist until the Sloan Digital Sky Survey. In 2005, Daniel Eisenstein and his colleagues worked through 46,748 luminous red galaxies, a bright uniform class that can be picked out reliably at great distance, spread across 3,816 square degrees of sky at an average redshift of 0.35. The bump was there, at the predicted separation, at the predicted size. A group using the 2-degree field survey on the Anglo-Australian telescope found the same feature independently that same year, in a different catalogue, using a different statistical method. What makes the result valuable is less the measurement itself than the list of things it does not depend on. A supernova distance rests on knowing how bright the explosion truly was, which rests on a correction calibrated against nearby examples, which rests in turn on the assumption that distant explosions resemble nearby ones. Every step is somewhere a systematic error could be hiding. The acoustic scale involves none of that. Nothing whatsoever has to be assumed about the brightness of anything. The length of the ruler is calculated from the physics of a hot plasma, which is understood about as well as physics ever understands anything, and using it is a matter of counting pairs and measuring angles. It is geometry rather than photometry, and it can be applied at many different distances at once, which turns a single ruler into a record of the expansion across billions of years. 3 of the 4 lines of evidence measure distance in one form or another. The 4th measures something else altogether. Gravity has been assembling matter into galaxies and clusters throughout cosmic history, and acceleration works directly against it. Once the expansion begins to quicken, any region that has not already collapsed is being pulled apart faster than gravity can draw it together. Structure formation slows, and then very largely stops. That produces a prediction with no reference to distance at all. Count the massive galaxy clusters at various epochs, and there should be fewer of them in recent times than a universe without acceleration would have built. Measure how clumpy the matter is, which can be done by observing the slight distortions in the apparent shapes of distant galaxies, whose light is bent as it passes the mass lying between them and us. And the clumpiness should have stalled at roughly the moment acceleration took hold. Both tests have been carried out. Both agree. The distinction matters more than it first appears. The other 3 establish that the expansion history has a particular shape. This one establishes that gravity is losing an argument at a specific rate. A theory that reproduced all the distances correctly but got the growth rate wrong would be caught by it, and some have been. Which brings us to the thing that actually settled the question. And it is not a photograph of anything. Draw a graph with the density of matter along one axis and the density of dark energy along the other. Every conceivable universe is a point somewhere on that sheet. A single measurement taken by itself does not identify a point. It identifies a long, narrow band of possibilities because each method is sensitive to some particular combination of the 2 quantities rather than to either one on its own. The supernova result constrains something close to the difference between them. Its band runs diagonally across the sheet and permits an enormous range of universes, very little of both, or a great deal of both, so long as the gap between them comes out right. The oldest light constrains the sum because the sum is what fixes the geometry. Its band crosses the sheet at very nearly a right angle to the first, and it also permits an enormous range. The acoustic ruler, read off the arrangement of galaxies, constrains a 3rd combination and lies at a 3rd angle again. Any one of those bands tells you almost nothing. 2 of them crossing narrows things considerably. All of them together intersect in a small patch near 30% matter and 70% dark energy. And there is nothing in the physics of exploding white dwarfs, the physics of a cooling plasma, or the statistics of where galaxies happen to sit that would conspire to put them in the same place. The intersection is the entire case, not any single result. the crossing. What none of it explains is timing. Dark energy does not dilute and matter does, so there must have been a period when matter was denser and gravity was still winning. The expansion ought to have been slowing for a very long time before it began to quicken, and somewhere between the two there should be a moment when the effects balanced and the universe changed direction. Locating that moment turned out to matter far more than it sounds, because the two serious objections to the whole result, dust lying in the way and supernovae that were simply different when the universe was young, both predict that distant objects grow steadily dimmer with distance and never turn back. A universe that decelerated first and accelerated afterwards predicts something quite different. Past a certain distance, the supernovae should start getting brighter again. The crossing itself was never in doubt. The only open question was when it happened. Two quantities were involved, and they were behaving in incompatible ways. The density of matter falls as the universe grows, dropping as the cube of the expansion spread the same material through 8 times the volume, and there is an eighth as much of it in every cubic meter. The density of dark energy does not fall at all. Whatever it was, it remains. One line descending steeply, one line perfectly level. Lines like that cross exactly once, and the only thing left to establish is where, which means nothing switched on. Dark energy did not arrive at some particular moment and begin pushing. It had been present the whole time, at the same concentration it holds now, exerting precisely the same influence per cubic meter when the universe was 1,000th of its present size. For most of cosmic history it was simply irrelevant, a rounding error alongside the matter, incapable of competing with it. It won by attrition. Everything else grew thinner, and it did not. There are, as it turns out, 2 crossings rather than one. If you have only ever been told about a single moment when dark energy took over, you were given the simpler of the two, and the difference between them matters. The obvious one is the moment the densities became equal, when there was as much dark energy in a cubic meter as there was matter. That happened surprisingly recently, somewhere around 3.5 billion years ago, by which point the Earth already existed and had oceans on it. But the expansion had begun accelerating well before that, and the reason returns to the peculiar way pressure enters into gravity. What decides whether the expansion quickens or slows is not the density on its own. It is the density plus 3 times the pressure. Matter supplies its density and essentially no pressure. Dark energy supplies its density and a pressure equal to minus that density, counted 3 times over. So its net contribution is not 1 unit of pulling inward, but 2 units of pushing outward. The consequence is that dark energy never needed to reach half the total in order to prevail. It needed to reach 1/3, and 1/3 arrived considerably earlier. Running the arithmetic with the measured densities places the turn at a redshift near 0.6, which works out at something in the region of 6 billion years ago. Direct measurements have landed at various points between roughly 1/2 and 8/10, depending on the method and the data set. The honest version of the answer is that the universe changed direction about 6 billion years ago, give or take, none of which would carry much weight if it could not be observed, and observing it was the entire point. Both surviving objections to the result had a particular shape. If intergalactic dust was dimming distant supernovae, the dimming would grow steadily worse with distance. More dust crossed, more light absorbed, no exceptions anywhere. If supernovae in the young universe were intrinsically fainter than nearby ones, that discrepancy would also grow steadily with distance, since the further back you look, the more different the stellar populations become. Both explanations produce a curve that only ever bends one way. A universe that decelerated first does something else entirely. Past a certain distance, the accumulated effect of the early braking overtakes the recent acceleration, and objects start appearing brighter than acceleration alone would predict. The curve turns over, Neither dust nor stellar evolution has any mechanism capable of producing a turnover. The object that settled it was found by accident and had been sitting in an archive. In December of 1995, the Hubble Space Telescope spent 10 days staring at a single unremarkable patch of sky near the handle of the plough, an area about the size of a grain of sand held at arm's length, and produced the deepest image anyone had ever taken. The same field was revisited 2 years later. Comparing the two sets of exposures, astronomers found a point of light in the later ones that had not been there before, in a galaxy lying far behind everything the observation had been designed to examine. Nobody had been hunting supernovae. If you had asked at the time what the deepest photograph ever taken would eventually be used to settle, this would not have appeared on the list. The images had been taken for completely different purposes, and by the time anyone worked out what the new point of light was worth, it had faded. What rescued it was that the telescope's infrared camera happened to have observed the same field afterwards, for reasons of its own, which meant a record of the fading existed. A light curve assembled entirely by chance out of observations nobody had coordinated. Adam Rees and his colleagues published the analysis in 2001. The supernova sat at a redshift of about 1.7. Its light had been traveling for something like 10 billion years, which meant it had detonated when the universe was around 4 billion years old, deep inside the era when gravity was still winning. It was too bright, not too faint, which is what a screen of dust would have produced, and equally what an intrinsically different population of exploding stars would have produced. Brighter than a universe coasting at a steady rate. Brighter than a universe filled with grey dust. Precisely as bright as a universe that had spent its early history slowing down before it began to speed up. 3 years afterwards, the same group used the telescope to build a proper sample rather than rest on a single object. 16 distant supernovae, 6 of them beyond redshift 1.25, and the turnover appeared in the data as a shape rather than a solitary point. The decelerating epoch had been observed directly, so the outline of the whole history is now known. For roughly its first 8 billion years, gravity was winning. The expansion continued because it had been handed an enormous initial rate and there was never sufficient matter to reverse it, but it was slowing throughout. The universe decelerating steadily, exactly as everybody in the 1990s had expected to confirm. Then, around 6 billion years ago, the matter had thinned enough for the balance to tip, and the expansion began to quicken. It has been quickening ever since. It will go on quickening, and the rate at which it quickens will itself increase because the thing driving it is not being used up. The Sun formed about 4.5 billion years ago. That is 1.5 billion years after the turn, which places the entire history of this solar system inside the accelerating era. The Earth assembled in it, the oceans condensed in it, every organism that has ever existed on this planet, every bacterium in the first shallow seas, every fish, every forest, every person who has ever stood outside at night and wondered what was going on out there, has lived its whole life in a universe that was speeding up. Nothing alive has ever known the other kind. That is a strange thing to be asked to accept, and the discomfort was not confined to people outside the field. Gravity, the one force everybody understood, had spent 8 billion years doing exactly what gravity does, and then lost, not to some stronger force, but to a property of empty space carrying the energy content of a few minutes of one power station spread through an entire planet. For 25 years, a considerable number of physicists have been trying, seriously and competently, to find a way out of it. General relativity has been confirmed to within a few parts in 100,000, and there is a detail about those confirmations worth pausing over, which is the size of the arena they were conducted in. The classic tests take place inside the solar system. Starlight bending as it passes the Sun, the slow precession of Mercury's orbit, the delay imposed on a radio signal grazing the Sun on its way back from a spacecraft. All of it across distances measured in light minutes and light hours. The most demanding tests of all come from binary pulsars, pairs of neutron stars orbiting one another so tightly and so regularly that the decay of their orbits can be tracked to a small fraction of a percent, and those systems lie a few thousand light-years away. Cosmology applies the same equations across 10 billion light-years. The extrapolation runs to something like a factor of 10 trillion beyond the regime where the theory has ever actually been checked. That is a legitimate reason for suspicion, and the people acting on it are not cranks. There is a respectable position which holds that the universe is not filled with an unidentifiable substance exerting negative pressure. The universe contains exactly what we can see, and gravity simply does not behave at the largest scales the way Einstein's equations claim. Alter the theory, and the acceleration falls out for free, with nothing new added to the inventory. A great many versions of this have been built. The technical approaches differ, replacing one term in the field equations with a more general function of it, constructing gravity out of a different geometric quantity altogether, or supposing that our universe is a surface embedded in a larger space, with gravity leaking away into the extra dimensions across great distances and weakening precisely where it ought to dominate. All of them run into the same immediate obstacle. Whatever you change has to leave the solar system untouched, because the solar system is where the theory has been verified to 5 decimal places. So the modification must be arranged to switch itself off wherever ordinary densities are present and assert itself only in the emptiest regions. This can be done, and there are mechanisms for doing it, but it takes deliberate engineering. It does not emerge naturally. The second obstacle is the growth of structure. A theory can be tuned to reproduce every distance measurement ever made and still get the rate at which galaxies assembled wrong, because changing gravity changes how quickly matter falls together, and that is measured independently. Several proposals have died on exactly that point. The third obstacle arrived on a single evening in August of 2017 from an observation that had nothing whatever to do with dark energy. 2 neutron stars merged in a galaxy roughly 130 million light-years away. The gravitational waves from the collision swept through the detectors at LIGO and Virgo. 1 3/4 seconds later, the Fermi Space Telescope registered a burst of gamma rays from the same position on the sky. After 130 million years in transit, gravity and light had arrived within 2 seconds of one another. That pins the speed of gravitational waves to the speed of light to within about 1 part in 1,000 million. A large share of the modified gravity theories then in circulation predicted that gravitational waves would travel at some other speed. They were built that way. For many of them, it was an unavoidable consequence of the modification itself. Within weeks of the detection, several independent groups had worked through the implications and published, and entire families of models that had been serious contenders for explaining cosmic acceleration were finished. Nobody had built LIGO to investigate dark energy. The instrument exists to detect colliding compact objects. It eliminated a substantial fraction of the alternatives to dark energy as a byproduct of doing the job it was designed for. A different line of attack leaves gravity entirely alone and argues that the error is in the arithmetic of averaging. The universe is only smooth if you squint at it. Across scales of hundreds of millions of light-years, it is roughly uniform, which is what the standard model assumes. On smaller scales, it is emphatically not. Matter is gathered into galaxies, clusters and filaments, and something close to half the volume of the present universe consists of enormous voids containing almost nothing at all. General relativity is a non-linear theory, and that has a specific consequence. Averaging a lumpy universe and then solving the equations is not the same operation as solving the equations and then averaging. The gap between those two procedures is called back reaction, and how large it is has been argued about for decades. David Wiltshire, working in New Zealand, has developed the most fully worked out version, which he calls the timescape model. It rests on a mathematical framework for averaging devised by Thomas Buchert, and adds a distinctly relativistic ingredient. Clocks run at different rates in different gravitational environments. A clock inside an empty void ticks faster than one inside a galaxy. Across billions of years, that difference accumulates, and Wiltshire's argument is that it accumulates to something in the region of 35%, meaning that observers embedded in matter, which is what we are, would systematically misread the expansion history of a universe whose volume is mostly emptiness. On that account, there is no dark energy at all. There is a lumpy universe and a calibration error. In December of 2024, a group including Wiltshire published an analysis of the largest available supernova catalogue and reported that the timescape model fitted the data better than the standard one did. If you have seen a headline announcing that dark energy does not exist, that paper is what it was about. The result is real, and the work is serious. It is also, at present, a fit to one of the four witnesses. The acoustic ruler written into the distribution of galaxies and the distortion of galaxy shapes by intervening mass have not yet been incorporated into the model. And until they are, what exists is an alternative account of the supernova data rather than an alternative account of the universe. The crossing point of independent measurements is the thing that has to be reproduced, and matching one of the bands is not the same as landing where all of them meet. There is also a considerable body of mathematical work by relativists arguing on general grounds that back reaction from small-scale structure cannot produce an effect remotely large enough to matter. That argument is not settled either. A third approach, now largely abandoned, proposed that we happen to be sitting near the center of an unusually empty region. Light arriving from outside would then have crossed zones expanding at different rates, which can be arranged to imitate acceleration without any acceleration taking place. The cost is what sank it. The void has to be hundreds of millions of light years across, and we have to be close to the middle of it, which reinstates precisely the sort of privileged position that 5 centuries of astronomy has been steadily dismantling. The oldest light rules it out fairly directly as well. An observer noticeably off-center inside such a void would see a characteristic distortion in the microwave background, and the distortion is absent. The idea has not quite died. It has been demoted to a smaller job, and now turns up mainly in attempts to explain a different problem altogether. 25 years of this has produced a consistent pattern. Every serious attempt to remove dark energy has managed to reproduce some portion of the evidence and then collided with a different portion. Change gravity and the growth of structure catches you, or a neutron-star collision does. Change the averaging and the acoustic ruler goes unexplained. Change our position in the universe and the oldest light contradicts it. None of the people involved were incompetent, and none of them were arguing in bad faith. They were doing what ought to be done with a result that requires 2/3 of reality to be something nobody can identify. The standard picture is still standing not because it went unchallenged, but because it was challenged repeatedly by capable people with every motive to succeed, and it held, which leaves the simple version in possession of the field. Empty space carries an energy. That energy does not dilute, and the universe is accelerating as a result. It is the least exotic option on the table. It fits everything. And it arrives attached to a calculation that produces the largest disagreement between prediction and measurement in the history of science. Take 2 flat metal plates uncharged and set them facing one another inside a vacuum chamber, roughly 1/millionth of a meter apart. They will be pushed together. Nothing is pushing them. There is no air between them, no charge on either surface, no field applied from outside. The plates move because of what is not there. Quantum field theory holds that the vacuum is not empty. Every field in nature, the electromagnetic field, the electron field, all of them, extends everywhere and is never entirely still. Even in its lowest possible state, a field retains a residual jitter that cannot be removed, because removing it would mean knowing both a value and a rate of change exactly, which quantum mechanics does not permit. Empty space is full of activity that has no source and cannot be switched off. Bring two plates close together, and the gap between them can only accommodate fluctuations whose wavelengths happen to fit. The space outside is under no such restriction. There is consequently slightly more activity outside the gap than within it, and the imbalance presses the plates inward. Hendrik Casimir worked this out in 1948. It was measured properly in 1997 using a torsion pendulum, and the force came out precisely where the calculation had put it. So the energy of empty space is not a conjecture. It has been weighed on a laboratory bench. What has never been weighed is the total. Every experiment in physics measures a difference. The energy released by a reaction, the gap between two levels in an atom, the change in a field when something passes through it. All of it is relative. The absolute energy of the vacuum never appears in any of these, because it sits identically on both sides of every comparison and cancels itself out. In practice, theorists subtract it away and proceed, and nothing whatever is lost by doing so, since nothing in a laboratory can detect it. Gravity is the exception. Gravity does not respond to differences in energy. It responds to energy. Whatever the vacuum's absolute density happens to be, it must bend space-time, and across the largest scales its effect should be plainly visible. Which makes cosmology the single place in all of physics where that number stops being an accounting convenience and becomes something you can actually measure. So somebody calculated what it ought to be. The procedure is simple enough in outline. Add up the residual energy in every mode of every field, across every wavelength. The sum runs to infinity if arbitrarily short wavelengths are allowed, so a cutoff has to be imposed. Some scale below which the theory is assumed to stop applying. The natural place to stop is the Planck length, around 1/100th of a billionth of a billionth of the width of a proton, where gravity itself is expected to turn quantum mechanical and the entire framework gives out. Perform the arithmetic with that cutoff and the energy density of empty space comes out at about 10 to the power of 120 times the value the universe actually displays. A 1 followed by 120 zeros. There are roughly 10 to the 80th atoms in the observable universe, a 1 with 80 zeros after it, counting every particle in every star in every galaxy anyone can see. The discrepancy exceeds that figure by a further 40 orders of magnitude. To reach the size of the error, you would have to take every atom in existence and count the whole collection through again 10,000 billion 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 times. Two qualifications are owed here, and neither of them helps a great deal. The first is that the 120 figure comes from the crudest available version of the calculation. A careful field theorist would not proceed that way. The machinery for handling infinities in quantum field theory is considerably more sophisticated than imposing a cutoff and totaling things up. Carried out more carefully, with the cutoff set at energies the theory is better trusted at, around the scales probed by particle accelerators for instance, the mismatch drops to something in the region of 50 or 60 orders of magnitude instead. 50 orders of magnitude is not a rescue. It is the difference between an error the size of the universe and an error the size of the universe. The second qualification is the more serious one, because the real problem is not the ratio at all. It is that the many separate contributions to the vacuum energy, and there are contributions from every field in nature, some positive and some negative, would have to cancel against each other almost perfectly, leaving a residue that first shows up somewhere around the 120th decimal place. No principle is known that would produce a cancellation like that. It has to be assumed, term by term, with no reason offered for any of it. The contrast with the rest of the theory is what makes this genuinely difficult to sit with. Quantum electrodynamics, the same framework resting on the same assumptions about fields and vacuum fluctuations, predicts the magnetic properties of the electron. That prediction has been checked against experiment to about 12 decimal places, and it holds. It is the most precisely verified statement in the whole of science, and it depends directly on those same vacuum fluctuations, which enter the calculation and are handled correctly. The framework gets the electron right to better than 1 part in a million and misses the energy of empty space by a factor with 120 zeros in it. Both answers come out of the same equations. There is one further turn to this, and it explains why the result of 1998 was received in some quarters with rather less delight than the newspaper coverage implied. Before the acceleration was found, everyone assumed the vacuum energy was exactly zero. That was awkward given the calculation, but it was a workable sort of awkward, because an exact zero is the kind of thing a symmetry can enforce. Symmetries compel quantities to vanish routinely. That is a large part of what they are for. The task was to identify the right one, and identifying it would have been a triumph. Then the measurement arrived, and the answer was not zero. It was extraordinarily close to zero, and it was not zero. That is a far harder number to account for. No symmetry produces it. A quantity that is minute but unmistakably present has no natural mechanism behind it, and the discovery of cosmic acceleration therefore took a difficult problem and made it considerably worse. Sitting alongside it is a second question, smaller in magnitude and stranger in character. Matter thins as the universe grows and dark energy does not, so the ratio between them has been changing continuously throughout cosmic history. When the oldest light was released, matter outweighed dark energy by a factor of several 100 million. In the distant future, dark energy will outweigh matter by factors with no practical limit at all. The ratio sweeps from one extreme to the other, and it passes through the neighborhood of 1 on exactly one occasion. At present, the two sit within a factor of about 2 of each other. There is no accepted explanation for why the era in which these measurements are being taken should happen to coincide with the brief interval when the two quantities are comparable. Proposals exist. Some of them involve reasoning about the conditions required for there to be observers at all, and none has reached consensus. The question has a name, the coincidence problem, and having a name is not the same as having an answer. A theory can survive an unexplained number. Physics has carried unexplained numbers around for a very long time. The masses of the fundamental particles are not derived from anything, and nobody treats that as grounds for discarding the rest of particle physics. A large open question is uncomfortable rather than fatal. What is much harder to live with is a measurement that has stopped agreeing with itself. Over the past decade, one of ours has. Only one of the two numbers is a measurement. That is the first thing to understand about the disagreement, and almost everything else follows from it. One of them is a measurement. You find nearby galaxies, establish their distances through the chain of techniques that has been under construction for a century, measure how fast they are receding, and divide. It is direct, it is local, and it assumes almost nothing about the history of the universe because the galaxies involved are close enough that the history has not had time to matter. The other is not a measurement at all. It is a prediction. The oldest light provides an extraordinarily detailed portrait of the universe at 380,000 years old. Fit the standard model to that portrait and its parameters are determined, the matter density, the amount of ordinary matter, the geometry, to remarkable precision. Once those are pinned down, the entire subsequent expansion history follows. You can run the model forward 13.8 billion years and ask what the expansion rate ought to be at the far end. Nobody has measured the present-day expansion rate with a microwave telescope. What has been done is to measure the infant universe and calculate forward through a model to now, which means that if the two disagree, there are exactly three possibilities. The local measurement is wrong, the early universe measurement is wrong, or the model joining them is wrong. They disagree. Planck's final analysis puts the prediction at 67.4 kilometers per second per megaparsec, with an uncertainty of half a unit. The local measurement from the group that has pursued it most doggedly comes in at 73.04 with an uncertainty of about 1. The gap is roughly 9%, which does not sound like much until it is converted into something with meaning attached. The two values imply ages for the universe that differ by about 1 billion years. In 2025, the local side of this was rebuilt from the foundations, and the rebuilding was deliberate in a way that matters. The trouble with a ladder is structural. Each rung is calibrated by the rung beneath it, so an error at the bottom is inherited silently by everything above. That architecture has failed before, twice, and on both occasions the failure was invisible from inside the structure for decades. A workshop convened in Bern in March of 2025, held under the title "What's Under the H0 Hood?", set out to replace the ladder with a network. Rather than a single chain running from parallax up through one class of variable star and outward to supernovae, the new framework links many distance indicators to one another at the same time. Cepheids, the tip of the red giant branch, mirror variables type 1a supernovae measured across the Hubble Space Telescope, the James Webb Telescope and Keck, and cross-connected wherever two techniques can be applied to the same galaxy. The difference is redundancy. In a chain, an error propagates upward and nothing contradicts it. In a network with several independent routes between the same 2 points, an error announces itself as an inconsistency because the routes stop agreeing. The result appeared in 2026, 73.5 give or take 0.8, a precision of just over 1%, the best local determination ever made. Set against the standard model as constrained by the microwave background, including data from the Atacama Cosmology Telescope and the South Pole Telescope alongside Planck, that sits 7.1 standard deviations away. Compared with a different early universe route entirely, the sound horizon calibrated by the physics of light element formation, combined with the acoustic ruler read off galaxy surveys. The gap is 5 standard deviations. 5 is the threshold at which physicists are permitted to announce that they have found something. The odds of a 5 sigma result arising by chance are about 1 in 3.5 million. This is comfortably past that, and it is not a discovery of anything. It is 2 answers to the same question, none of which settles the matter, because there is a substantial and entirely serious dissent. Wendy Friedman, who ran the project that produced the 72 figure a quarter of a century ago, has argued for years that the Cepheid route carries a problem which has not been adequately dealt with. Cepheids are young, massive stars, and young massive stars sit in the crowded, dusty regions where they formed. Even at the resolution of the James Webb Telescope, light from neighboring stars can blend into the measurement and make a Cepheid look brighter than it is, which makes its galaxy look nearer, which drives the expansion rate up. Her group has pursued alternatives that avoid the difficulty by using different stars altogether. The tip of the red giant branch relies on old stars in the outer halos of galaxies, where crowding is minimal and dust is scarce. A second method uses a particular class of aging star with the same advantages, Applied to James Webb observations, those two approaches return 68.8 and 67.8, both sitting comfortably beside the early universe prediction. Her own assessment is direct. The evidence based on these data, she has said, does not suggest the need for additional physics. The other camp has replied in kind, identifying a missing term in the uncertainty budget of that analysis, and arguing that the number of supernova host galaxies with primary distance measurements is still too small for the comparison to be decisive. James Webb has now re-observed 19 of the 37 galaxies anchoring the higher result. The remaining 18 have not yet been done. It is entirely possible that the disagreement between the two groups dissolves once the sample is complete. It is also possible that it does not. Two other approaches step around the argument by using neither Cepheids nor supernovae. Some galaxies contain clouds of water molecules orbiting their central black holes and emitting microwaves in a narrow beam. Tracking those clouds yields a distance from pure geometry, with no ladder involved anywhere. And when a distant quasar happens to sit behind a massive galaxy, its light reaches us along several paths of unequal length, so any flicker in the quasar appears in each image at a different moment, and the delays between them encode the distance. Both have returned values on the high side, in the low 70s, with larger uncertainties than the ladder produces. They are not precise enough to settle anything. They are precise enough that the high value cannot be blamed on Cepheids alone. If the answer turns out to be new physics rather than an undetected error, the most likely place for it is a quantity that has already appeared in this account. The expansion rate inferred from the early universe depends almost entirely on the sound horizon, the distance those pressure waves managed before the fog cleared. That length is a ruler, and the inferred rate is essentially a statement about how large the ruler appears from here. Shorten the ruler and the inferred rate goes up. Nearly every serious proposal works that way. The most heavily studied version posits a brief episode of something dark energy-like acting shortly before recombination, which would quicken the expansion at that moment, leaving the sound waves less time to travel and shrinking the horizon by the required few percent. The difficulty is that the early universe is not underdetermined. It has been measured in considerable detail, and adjusting it to fix one number tends to break others. Proposals that raise the inferred expansion rate generally worsen the fit to the clustering of matter, or to the fine angular structure of the microwave background, or to the abundances of the light elements. There is at present no proposal that resolves the disagreement without opening a new one somewhere else. What makes this genuinely hard is a pattern rather than any single figure. When a disagreement of this kind appears, the expected outcome is that improving precision on both sides exposes the systematic error and the values converge. That is exactly what happened the last time the expansion rate was catastrophically wrong. The calibration errors were eventually found, the number came down by a factor of 7, and it stopped moving. The opposite has happened here. Both sides have improved substantially across 15 years. The uncertainties have shrunk on both, and the disagreement has not narrowed at all. It has sharpened because the same gap divided by smaller error bars is a larger discrepancy. Every gain in precision has made the problem worse. If your instinct is that somebody has simply made a mistake somewhere, that is a reasonable instinct, and it is shared by essentially everybody working on it. They have been hunting for the mistake for more than a decade, and they have not found it. So there are two live possibilities, and the field is genuinely divided between them. Either a systematic error is hiding inside a measurement chain that hundreds of people have now been over repeatedly, or the standard model of cosmology is missing something between the early universe and the present day. If it is the second, the missing piece need not be back at the beginning at all. It could be at this end, inside the one assumption that has been running quietly underneath every calculation in this story without ever having been tested directly. The assumption is that dark energy is a constant, that it has always had the same value, that it has never varied, and that it never will. In the spring of 2024, a survey built specifically to test that assumption reported that it might not be true. There are 5,000 of them, and every 20 minutes they all move at once. Each is a small robotic arm holding the end of an optical fiber, packed into the focal plane of a 4-meter telescope on Kitt Peak in Arizona, an instrument built in the early 1970s and handed an entirely new purpose. Between exposures, all 5,000 reposition themselves in about 2 minutes, each placing its fiber precisely onto the image of one specific galaxy or quasar. Then the shutter opens and 5,000 spectra are recorded at the same time. A century ago, obtaining the spectrum of one faint galaxy took 80 hours of accumulated winter darkness, and a man holding it steady by hand. This machine collects 5,000 every 20 minutes and has now catalogued distances to more than 50 million galaxies. Its purpose is narrow. It is not searching for anything. It is measuring the acoustic ruler, that fixed separation left behind by the pressure waves in the infant universe, at a great many different distances, which is to say, at a great many different moments in the past. One measurement of the ruler gives a distance. Measurements at a range of depths give the expansion history, and the expansion history is where dark energy keeps its record. If its density has been constant for 13 billion years, the ruler will appear at exactly the sizes a constant predicts. If it has not, the sizes will drift. Testing that meant loosening an assumption which had been in place from the beginning. The ratio of pressure to energy density is exactly -1 for a cosmological constant, and every analysis up to this point had simply fixed it there. There was no evidence for anything else, and no reason to add a free parameter without evidence. To ask whether it varies, you permit 2 numbers in place of 1, its value now and the rate at which it has been drifting. Then you let the data choose. In April of 2024, working from its first year of observations, DESI reported that the data preferred a drift. The preferred solution had a specific shape, and the shape is the interesting part. Dark energy appeared to have been stronger than a cosmological constant in the distant past, and weaker than one at present. Not steady, fading. That first preference was modest, around 2.5 standard deviations, which in this field is the level at which people become curious rather than persuaded. When the second data release arrived in March of 2025, built on 3 years of observations, it had grown. Taken with the microwave background alone, the preference for a changing dark energy stood just above 3 standard deviations. Combined with catalogues of Type 1a supernovae, it ran higher still, reaching 4.2 depending on which catalogue was used. 4.2 commands attention. The coverage was extensive and it was not unwarranted because the implications are large. If dark energy is weakening, it is not Einstein's constant. The vacuum energy interpretation is finished. Whatever drives the expansion is a field of some kind with its own behavior, and that would be the most consequential development in cosmology since the acceleration was discovered. One technical reservation was worth noting even then. A dark energy stronger than a cosmological constant in the past, and weaker now, must have passed through exactly -1 somewhere along the way, and crossing that particular value is awkward to arrange. The simplest field models cannot manage it at all. It takes either more than one field or something distinctly less tidy. The result was interesting partly because it was so difficult to build. Then the people holding one of the supernova catalogues went back and examined their own instrument. The Dark Energy Survey had spent 5 years accumulating Type 1a supernovae. and its 5-year sample was among the catalogues driving the higher figures. In November of 2025, the collaboration published a reanalysis of its own data. They had found several problems. The photometric calibration linking their measurements to those of other surveys needed rebuilding, and they reconstructed it using observations of white dwarfs as a shared reference. The model used to fit supernova light curves was retrained from scratch, and there was an error in the code, a numerical approximation inside the calculation that converts a supernova's observed color into a brightness correction, a calculation which also depends on properties of the galaxy the explosion happened in. The corrected sample holds about 1,600 supernovae from the survey, together with roughly 200 nearby ones. Recalibrated, the matter density of the universe came out about 2/100ths lower than the previous analysis had placed it, and the evidence for changing dark energy weakened. Combined with the microwave background and the DESI measurements, the preference fell from 4.2 standard deviations to 3.2. The author's own summary of what survived was that the data now show only a weak preference for evolving dark energy. A numerical approximation inside a piece of analysis software had been carrying roughly a quarter of the statistical case for how the universe ends. 9 months later, the most sensitive measurement DSI is capable of arrived, and it did not clarify matters. When light from a very distant quasar crosses the space between there and here, it passes through innumerable clouds of neutral hydrogen. Each cloud absorbs at one precise wavelength, and because every cloud lies at a different distance and therefore a different redshift, those absorption lines land at different points across the quasar's spectrum. The result is a dense picket of dark notches, effectively a core sample of the hydrogen along one line of sight, reaching back far earlier than any galaxy survey can go. Collect hundreds of thousands of such sight lines and the acoustic ruler can be measured in the distribution of hydrogen itself at epochs long before the galaxies DESI otherwise uses had assembled. Those results were released on the 30th of July, 2026. Taken with the microwave background and the galaxy measurements, the preference for a changing dark energy came in around 3 standard deviations, consistent with what had been reported before. Combined with the supernova catalogues, it largely dissolved. How much survived depended heavily on which catalogue was used, and across the plausible combinations, the preference mostly fell to levels that would convince nobody of anything. The collaboration's own conclusion, stated in the paper, was that it remains too early to rule out the standard model. So, the position as it actually stands is worth setting out plainly, because it is not the position 2 years of headlines would suggest. Nothing has reached 5 standard deviations. Nothing is near it. The strongest combinations sit between 3 and 4. The weakest sit close to 1, and the spread between them tracks which supernova catalogue happens to be included, which is precisely the pattern that indicates a systematic effect rather than a discovery. 3 standard deviations is roughly the confidence at which a sensible person might rearrange the furniture. It is a very long way short of what is needed before rearranging the universe. If you followed the coverage in 2024 and 2025, you will have seen the announcements. What happened next made almost no news at all. The team holding one of the decisive datasets went back through its own calibration, found the errors, and published a result that undercut the most exciting reading of their own work. None of it will stay unresolved for long, which is unusual for a question of this size. On the 30th of June 2026, the Vera Rubin Observatory in Chile began a survey it will run for 10 years, photographing the whole of the southern sky every few nights with the largest digital camera ever built. During commissioning, on a single night in February, it generated 800,000 alerts for objects that had changed since the previous pass. The analysis published as it came into operation projects that 1 year of its gravitational lensing data will reach a precision comparable to DESI's entire survey. The same question, approached by a completely different method. Euclid, launched by the European Space Agency in 2023, releases its first cosmology results in October of 2026. And the Nancy Grace Roman Space Telescope is scheduled to launch on the 30th of August, 2026, on a Falcon Heavy from Florida, the date having been brought forward by 8 months from the original commitment. It carries a mirror the size of Hubble's and a field of view roughly 100 times wider, and it will survey something on the order of 1 billion galaxies. Science operations begin in early 2027. As this is being recorded, that telescope is on the ground, fueled, waiting for a window. 3 instruments, 1 question, and an answer that should arrive within a decade rather than a century, which matters more than a parameter usually does. If the ratio is exactly -1, dark energy is a constant, it will never weaken, and the expansion will accelerate without limit for as long as there is a universe to accelerate. If it is drifting upward, the acceleration will ease and might eventually stop altogether. If it is drifting the other way, downward past -1, the acceleration grows steadily more violent and the universe has a finite remaining lifespan that can be written down in years. That number decides which of those happens. It is being measured now. Most of the galaxies in a deep photograph are already beyond reach. They are visible. Their light is arriving tonight and will go on arriving for a long time yet, but the light leaving them now will never get here. Somewhere in between, the expansion has opened a gap that light cannot close, and everything those galaxies do from this moment onward lies permanently outside anything we could ever observe. The boundary sits at around 16 billion light-years, measured the way cosmologists measure distances across an expanding universe. Anything beyond it has already crossed. The deep images reach out to 46 billion, which means that the overwhelming majority of galaxies ever catalogued are objects we are watching in the past tense. We can see what they were. We will never learn what became of them. They do not blink out when they cross, and that is worth being precise about, because the intuitive picture is of lights going off one by one, and it is not what happens. As a galaxy approaches the horizon, its light stretches further and further toward the red, and the rate at which we see it living slows down. Its stars appear to burn more slowly. Its rotation winds down. The image dims without limit and holds, effectively frozen at the moment of crossing, draining toward a color no instrument can register. Nothing switches off. Everything simply stops and fades and stays. What happens after that depends on the number currently being measured. If the ratio is exactly -1, if dark energy really is Einstein's constant, unchanging, a fixed property of space, then the process just described runs on without interruption, and the ending can be calculated. The Milky Way and Andromeda will begin to collide in about 4 billion years and finish merging a few billion years after that. The rest of the local group follows them in. What remains is a single large elliptical galaxy, bound by its own gravity, taking no part in the expansion. Everything outside it goes. By the time the universe is around 100 billion years old, nothing beyond that one galaxy will be observable from within it. Not faintly, not with better instruments, not at any wavelength or any magnification. There will be nothing there to see. 100 billion years is not an incomprehensible stretch of time. It is roughly 7 times the age the universe has already reached. Inside the surviving galaxy, ordinary physics carries on for a very long while. Stars keep forming as long as there is gas to form them from, which is somewhere between 1 and 100 trillion years. The smallest red stars burn slowly enough to last most of that. Eventually the gas is exhausted, The last stars cool, and what is left is a population of dead remnants, white dwarfs going dark, neutron stars, black holes, drifting through an unlit galaxy that slowly comes apart as its members trade energy and a few are flung out. The black holes are the last things standing, and they go too. A black hole the mass of a star takes something like 10 to the power of 67 years to evaporate. Written out, that is a 1 followed by 67 zeros against a universe that has so far existed for about 10 to the power of 10. If the ratio sits below -1, if dark energy is not constant but strengthening, the ending is very much shorter and considerably less patient. Dark energy whose density rises as the universe grows becomes steadily more dominant, and its influence eventually reaches down through every scale. For an illustrative value of -1.5, the arithmetic was worked through in 2003 by Robert Caldwell, Mark Kamionkowski, and Nevin Weinberg, and the universe ends about 22 billion years from now. It comes apart in order of how tightly things are held. Clusters of galaxies unbind roughly 1 billion years before the end. The Milky Way is pulled apart around 60 million years before it. The solar system comes undone a few months out, the Earth some minutes after that, and atoms in the final fraction of a second. That is one scenario, corresponding to one specific value of one specific number, and the present measurements do not favor it. It is here because it is what the equations produce if the number falls on that side of the line. And if the ratio is drifting the other way, upward towards 0, which is the direction the recent hints have pointed, then dark energy is weakening. The acceleration eases. With enough weakening, it stops entirely. And if it reverses far enough, gravity takes the universe back and everything falls together again. The timescales there depend completely on which model is assumed, and they range from the merely enormous to the practically unbounded. 3 endings separated by one quantity being measured this decade by 3 instruments. There is a further consequence of the first of them, and it is stranger than the ending itself. In 2007, Lawrence Krauss and Robert Scherer published a short paper working out what cosmology would look like to observers living in that final galaxy, assuming there are any, which is a separate question. Everything in this account rests on 3 observations: the expansion of the universe, the microwave background, and the abundances of the light elements manufactured in the first few minutes. Those 3 are the evidence from which the entire history was reconstructed. Take them one at a time. The expansion is measured by watching other galaxies recede. When there are no other galaxies, there is nothing to measure. An observer in that elliptical would find a sky containing one galaxy's worth of stars and no external objects of any kind, and would have no reason whatever to suppose that space was doing anything. The microwave background does not disappear, but it stops being detectable. Its temperature falls as the universe grows, and its wavelengths stretch until they run past anything an instrument sitting inside a galaxy could register. The oldest light will still be there, still arriving. There will simply be no way to notice it. The light elements are erased by ordinary stellar chemistry. The primordial helium fraction is a fingerprint of the first 3 minutes, and it is readable now only because the universe has not yet processed very much of its hydrogen. After 100 billion years of star formation, the gas in that galaxy will have passed through so many stellar generations that the helium made by stars completely swamps the helium made by the early universe. The fingerprint is not destroyed. It is buried under a much larger signal of an entirely different origin. So the observers in that galaxy will look out carefully with good instruments and find a single island of stars in empty space, apparently unchanging, with no relic radiation and no sign of any beginning. They will conclude that the universe consists of one galaxy, static and without age. It is precisely the picture Einstein started from in 1917, and every observation available to them will support it. They will not be careless, and they will not be stupid. They will be doing exactly what we are doing with the evidence they have. And they will be wrong, and there will be no way from inside that galaxy to find out. Which leaves us somewhere unusual, and it is worth sitting with for a moment before this ends. We are not anywhere special. That has been established repeatedly and at considerable cost. The Earth is not the center, the Sun is not the center, this galaxy is not the center, and there is no center. Every search for one has failed, and the failures were the discovery. But nothing guarantees that all moments are equivalent, and this one is not. We arrived late enough that there were instruments and mathematics, and people willing to sit in an unheated dome through 80 hours of winter for a single measurement. And we arrived early enough that the light is still coming in, that the galaxies have not yet gone, that the oldest radiation is still warm enough to register, that the helium from the first 3 minutes is still legible underneath everything that has happened since. Both of those had to be true at the same time. They will not both remain true. Not on any scale that matters to a human life, but the window is finite, and it began closing some time ago. The uncomfortable part is that we cannot be sure we are not already inside the closing. If something was observable 8 billion years ago and has since slipped past recovery, nothing in our data would record its absence. We would simply have a slightly smaller universe than we believed, and no way of knowing the difference. Every generation of observers gets the sky it is handed. What can be said is that at this particular moment, in this particular corner, matter that had been arranging itself for 13 billion years worked out where it came from, and roughly how it ends, and how much of it there is, and managed it while the evidence was still on the table. That is not a small thing to have happened. It is also not permanent. So here is where that leaves you tonight. You are made from the smallest category in the whole inventory. Ordinary matter, the 5%, and within that, the fraction which is not thin gas drifting between galaxies. Rock and water and carbon and iron, which is close to the rarest arrangement available anywhere. The iron is worth a moment. Roughly half of all the iron in the universe was made in exactly the kind of explosion this entire measurement was built upon. A white dwarf about the size of the Earth, reaching a mass it could not hold, converting itself in 2 seconds into a cloud of new elements. Those explosions are how the expansion was measured. They are also where the iron in your blood came from. The same objects, doing the same thing for reasons that have nothing to do with each other. Light is arriving at you right now from galaxies that are already beyond reach. It left before the gap opened, and it has been traveling ever since, and it will go on arriving for billions of years after those galaxies have fallen silent. There is a great deal of it still in transit. None of it requires anything from you. The measurement continues either way. Somewhere there is a telescope on the ground in Florida waiting on the weather, and a survey turning quietly through the night in Chile, and an instrument on a mountain in Arizona doing the same patient thing it does every night, whether or not anyone is awake for it. There is nothing here you need to hold on to, nothing to remember and nothing to decide. Rest now. The universe has been doing this for 13 billion years without supervision. It will manage a few more hours. Good night.